Ya. So everything okay ya di Malaysia ya, sudah membaik ya?
Yeah, still lockdown.
Still lockdown.
Still lockdown.
The same.
Still lockdown mean not good. Same with Indonesia.
Always, Prof. Alan Tan, how are you?
I'm good. I'm good. Mystery.
How's the situation there?
I'm based in Tokyo now. So
Tokyo.
yeah, I'm Tokyo now. Still in Tokyo.
Yeah, Nihongo aresmashou ka?
いいよ。いいですよ。
はじめまして、ヘリと申しますが、よろしくお願いします。
Professor Henry, you speak Japanese?
Yeah, 1990 to 1993, I studied at Japan. I mean, at Keio University.
Okay.
So I'm a Keio boy.
Keio, okay.
Keio alumni, we call it Keio boy.
I've been here 20 years, 21.
Oh, 21 years?
Yeah, too long.
Oh,
Okay.
So, Nihongo pera-pera desu ne.
Yeah.
Dean Henry, I only know one word in Japanese. Very fluent.
What?
Gambate.
Konnichiwa.
Konnichiwa.
I hope next year will be offline.
Yeah, everybody hope Mr.
Yes, I think the committee would like to initiate it.
Okay.
So we should let the... Ya, silakan Mbak Tika.
Okay.
Pak Zaki, Pak Zaki.
Sorry to interrupt, ladies and gentlemen, but I think we can start the opening ceremony now.
Yeah, sure. Please.
Okay. Ladies and gentlemen, may I have your attention, please? The opening ceremony of the International Symposium of Biomedical Engineering 2021 will now begin. Please make sure that you have adjusted your username in accordance with the name used for registration. And we kindly request all guests and participants to please mute their Zoom account to prevent additional noise during the opening ceremony. At the end of the opening ceremony, we will have a photo session. Please make sure that you turn on your camera for the photo session. Ladies and gentlemen, welcome to the virtual International Symposium on Biomedical Engineering 2021. With the continuous rise of the COVID-19 in Indonesia, we once again have to abide to the protocol where we interact virtually while maintaining the COVID-19 health protocol. Thank you to all speakers and participants for making the time to join us virtually. Ladies and gentlemen, this year's symposium will focus on empowering multidisciplinary partnership for healthcare product industry and services. Please welcome to the screen the General Chair of International Symposium Biomedical Engineering 2021 Organizing Committee, Dr. Ahmad Zakiyuddin, Sarjana Teknik, Master of Engineering, to give his report. Dr. Zakiyuddin, the screen is now yours.
Thank you very much, Mbak Tika. Hi everyone, good day. Assalamualaikum warahmatullahi wabarakatuh. Peace be upon you and God's mercy and blessings. The Honorable Dean of Faculty of Engineering Universitas Indonesia, Associate Prof. Henry Dias Budiono, the Honorable Assistant Vice Chancellor, College of Engineering, Universiti Teknologi MARA, Malaysia, Professor Senior Engineer Dr. Suhaimi Abdul Talib, the Honorable Director of RCBE, Associate Professor Yudan Wulanza, the Honorable Keynote Speaker, Professor Chow Ling Yao, Dr. Alan Tan, Professor Kamarza Mulia, Dr. Rifa Ichai, and Dr. Izhar Aziz. Thank you for your valuable time sharing current issues in biomedical engineering combating, especially in this second year of COVID-19 pandemic situation. And also the Honorable of ISBE 2021 participants. On behalf of organizing and steering committees, it is my great pleasure and privilege to welcome you to the 6th of International Symposium on Biomedical Engineering, or Isbe 2021, empowering multidisciplinary partnership for healthcare, product industry, and services. Today, collaborative work from various disciplines is important to realize research into a product that benefits and significantly impacts society. The growth of multidisciplinary research in the last few decades of the 20th century where academics from several disciplines collaborate and each draws on their disciplinary expertise. This approach has made significant progress, but some of the most difficult challenges require greater integration of the disciplines, such as sharing and merging methods, knowledge, and frameworks from many disciplines, such as collision, have resulted in significant progress and groundbreaking innovation in fields ranging from synthetic chemistry to genomic. Isbe is an annual conference of research center for biomedical engineering that aims to gather researchers in the biomedical engineering fields to share and hopefully collaborate in the near future. This year is the second year of Isbe held using online platform due to the global pandemic of COVID-19. Hopefully, it will not reduce the quality of work and interaction and collaboration among participants. Especially COVID-19 is a global challenge that should be solved across nation. The online plenary and parallel session conducted using Zoom meeting, and also during the break, we provide a breakout room for intensive discussion, and also the plenary session can be accessed via YouTube live streaming of the Faculty of Engineering Universitas Indonesia. In this Isbe 2021 has plenary session that present 5 wonderful keynote speakers. Professor Chao Ling Yao from Yonsei University of Taiwan, with his topic expansion and differentiation of cord blood hematopoietic stem cells for cell therapy and immunotherapy. Dr. Alan Tan from Dassault Systems, Singapore, with his topic virtual human modeling. Prof. Kamarza Mulia from Faculty of Engineering Universitas Indonesia, with his topic green extraction, encapsulation, and controlled release of drugs or bioactive compounds. Dr. Rifai Chai of Swinburne University of Technology, Australia, with his topic toward interdisciplinary research of brain technology for medical devices. The last keynote speakers, Dr. Izhar Aziz of Managing Director of 3D Gens, with his topics additive manufacturing for biomedical application. Isbe 2021 is also having invited speaker Muhammad Taufikur Rahman, PhD candidate from University of Leeds, United Kingdom, Kenny Vidilaseris, PhD from University of Helsinki, Finland, Maria Fomero, PhD from Columbia University, United States of America, Dr. Rifki Ismail from Diponegoro University, Indonesia, Giska Ramahdita from Washington University in St. Louis, USA, and Associate Professor Dr. Engineer Shahrul Azam Abdullah from Universiti Teknologi MARA, Malaysia. This year also, Isbe 2021 is sponsored by Worley and the Dassault system, and it is our pleasure to receive around 85 submissions in total throughout, come from Indonesia, Japan, Germany, Mongolia, Netherlands, South Korea, and also United Kingdom. The conference topic covers biomaterials, medical devices, clinical and public health, and also drug delivery. All the presenting papers of Isbe 2021 will be published in AIP proceeding. We will also announce the best presenter in the last days of during the closing ceremony of the conference. Please make sure to follow every session until the end of the closing ceremony, and please make your best effort to present the paper. Finally, I would like to thank the College of Engineering of Universiti Teknologi MARA, Malaysia as the co-host of Isbe 2021 and Worley Dassault System as our platinum sponsor. Hopefully, from this conference, we can obtain a fruitful benefit as well as make a strategic collaboration in the near future. I sincerely hope you will enjoy today and tomorrow's discussion, networking among the participants. Have a wonderful conference day. Wassalamualaikum warahmatullahi wabarakatuh.
Ladies and gentlemen, today's symposium will not be possible without the full support from the Faculty of Engineering Universitas Indonesia. Please welcome Associate Professor Dr. Henry D.S. Budiono, Dean of Faculty of Engineering Universitas Indonesia, to deliver his opening remark. Dr. Henry, the screen is now yours.
Thank you, Mrs. Tika. Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. May prosperity be upon us all. Om Swastiastu, Namo Buddhaya, greeting of virtue. Ladies and gentlemen, good morning to you all. Honorable my colleagues, Professor Insinyur Dr. Suhaimi Abdul Talib, Assistant Vice Chancellor, College of Engineering, Universiti Teknologi MARA, Malaysia. Director of RCBE, Dr. Yudan Wulansa, General Chair International Symposium on Biomedical Engineering, Dr. Ahmad Sakiuddin, as the Master of Engineering. Thank you for your very detailed report. Our esteemed keynote and invited speaker, sorry, I cannot say your name one by one according to the time limit. All participants and guests of the International Symposium on Biomedical Engineering, or we always called Isbe 2021. It is my great pleasure that I welcome the participant of the International Symposium on Biomedical Engineering 2021. The quest for knowledge has been from the beginning of time, but knowledge only becomes valuable when it is disseminated and realized to benefit humankind. This quote on transforming idea into reality has influenced the role of collaboration among multidisciplinary fields in the development of the nation. Faculty of Engineering Universitas Indonesia established the Research Center on Biomedical Engineering, or we call it RCBE, in 2015. Currently, RCBE plays a strategic role as an interface between science and medicine. Engineers and scientists are the backbones of technology development, and clinicians are key in the application of the technology. Emerging engineering and medical field toward human is a very significant contribution to solving a problem in society. Faculty of Engineering Universitas Indonesia has contributed to the fight against COVID-19 since the beginning. Last year, Faculty of Engineering Universitas Indonesia has developed and distributed several COVID-related products such as movable hand washer, disinfectant chamber, Indonesian propolis for COVID-19, flock swab chamber, ventilator UI Coven 20. With this year, we will launch the high flow nasal cannula and e-thermal wall. It is anticipated that the intellectual discourse will result in the future collaboration among universities, research institutions, and industries, both locally and internationally through Isbe 2021. In particular, it is expected that the focus will be given to issues on the development of biomedical engineering. It is hoped that Isbe 2021 will be a platform to gather and disseminate the latest knowledge in medical and engineering. academicians, scientists, researchers, and practitioners of engineering will be able to share and discuss new findings and application of the current situation, especially global challenges faced due to the COVID-19 pandemic. This is the reason we all gather here today. Old colleagues, academic peers, and new friends to talk about old topic or brand new issue that we might never heard of before today. Even though the pandemic forces us to connect virtually through online platform, we hope that this condition will not deter us and will motivate us to make more progress in biomedical engineering. Today in the 6th Isbe, we will hear and hopefully be inspired by speakers from Taiwan, Singapore, Indonesia, Australia, and Malaysia that will share with us the cutting edge of current trend technology in biomedical engineering. Let us remember that this very moment of united engineering and medical in answering the challenges on biomaterial, medical device, and drug delivery, and combating COVID-19. We have succeeded in establishing dialogue as well as a network of bilateral and regional association agreements. I would like to thank our colleagues from Universiti Teknologi MARA, College of Engineering, and Dassault Systems PT Limited Singapore for their gracious support. Additionally, I extend a heartily thank you to the member of the organizing committee for dedicating their valuable time for preparing this conference. May have a successful, stimulating, fruitful, and rewarding conference. Thank you. Wassalamualaikum warahmatullahi wabarakatuh. Back to Mrs. Tika.
Thank you, Dr. Henry. Ladies and gentlemen, each year the International Symposium on Biomedical Engineering tries to expand our partnership by inviting other universities to join us to co-host our symposium. This year, we are honored to have the opportunity to host the symposium with the College of Engineering, Universiti Teknologi MARA, Malaysia. Please welcome to your screen, representing Universiti Teknologi MARA, Assistant Vice Chancellor of College of Engineering, Professor Surveyor Insinyur Dr. Suhaimi Abdul Thalib. Professor, the screen is now yours. You are still muted, Professor Suhaimi.
Thank you. Thank you for reminding me. Thank you, Ms. Tika. Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Salam sejahtera and a very good morning. Allow me to acknowledge my honorable colleague, Insinyur Henry Dwi Saptioratria Budiano, Dean Faculty of Engineering, Universitas Indonesia, Dr. Ahmad Zakiuddin, General Chair of RCBE 2021 from Faculty of Engineering, Universitas Indonesia, and Pak Yuden Ula, the head of Research Center for Biomedical Engineering, Pak Yudan, and also Associate Professor Dr. Muhammad Hussein Ismail, Head of Linkages, College of Engineering, Universiti Teknologi MARA. And allow me also to acknowledge our keynote speakers, Professor Chow Ling Yao from Taiwan, Dr. Alan Tan from Singapore, Professor Kamar Zamulia from Indonesia, Dr. Rifai Chai from Australia, and Dr. Ishar Aziz from Malaysia. Representatives from universities and industries, distinguished guests, ladies and gentlemen. It is my pleasure to acknowledge our hosts from Universitas Indonesia, particularly Research Center for Biomedical Engineering, and the co-hosts from Biomedical and Clinical Engineering Research Group of UITM, as well as our respective partners from universities and industries on this virtual event, the 6th International Symposium on Biomedical Engineering, ISBE 2021. On behalf of the College of Engineering, UITM, I would like to take this opportunity to thank Universitas Indonesia for inviting us to co-host ISBS for the second time after the first event in 2020. This two-day event starting today has marked another milestone for both research teams from Universitas Indonesia and UiTM, particularly in the area of biomedical and biomechanical engineering in the strategic partners from related industries. ISBE 2021 this year is conducted virtually against the background of the global struggle in containing the COVID-19 pandemic. It warms my heart to hear Pak Henry just now mentioning the contributions made towards fighting the COVID-19 pandemic in Indonesia, with various products and services being developed by the research departments at Universitas Indonesia. Multiple precautionary measures, such as having this virtual event, have to be taken in order to prevent further spreading of the virus. Though we have this virtual event, I hope I share the same aspiration as Pak Henry. We hope that the virtual event will not diminish the quality of the knowledge sharing sessions that we are about to have in these 2 days. Through this collaboration, I sincerely look forward to Universitas Indonesia and UiTM working closely together with our strategic partners in academia and the industry to actively strategize, explore, and share technology advancement, particularly in biomedical engineering, embracing Industry 4.0. There is an urgent need to capitalize on the advances in technology and medical knowledge to produce even more breakthroughs for our society and community. Moreover, this collaborative event aims to strengthen the bonds and cooperation between UiTM and Universitas Indonesia. For universities, research collaborations are crucial as they encourage stimulating collaboration and also serve to bridge innovative research with commercialization. In dealing with the complexity of the future, our thinking must change. We must adopt scenario planning and foresight analysis in order to cope with the disruptive technologies. Our life have been disrupted in many ways. Perhaps this is the time that we should consider of bringing in new disruptive technologies that originate from the researchers of UiTM and also Universitas Indonesia. In Malaysia, strengthening national research capacity and capability is one of the key agenda of the government. Matching grants are being strategized by the research management centers of both Universitas Indonesia and UiTM. This includes effort through Strategic Research Partnership, SRP, and the Bilateral Strategic Alliance, BISA, which aim to provide a platform for investment in expanding and enhancing research capacity and increasing collaborative R&D partnership. These partnerships are to focus on projects that are innovative, giving high impact, and subsequently contribute to the advancement of knowledge and technology development leading to commercialization. I am happy to note that a number of research proposals has been submitted, and we look forward for the opportunity for both UiTM and Universiti Indonesia to work in a synergistic manner. I am confident through these synergistic efforts, we will be able to achieve more, and we will be able to continue to develop even stronger relationships and friendships between us. I am sure that this collaboration will continue to flourish into fruitful relationship that will contribute in a much more significant way. Hence, I hope this collaborative effort can progress harmoniously and will do so at an even faster rate. In closing, I would like to graciously thank our partners from Indonesia and Malaysia for your commitment. Thus, I would like to take this opportunity to offer my sincere appreciation to members of the organizing committee from both Universitas Indonesia and UiTM for working towards ensuring the success of this event. Thank you very much. Assalamualaikum warahmatullahi wabarakatuh. Back to you, Ms. Tika.
Thank you, Professor Suhaimi. Ladies and gentlemen, before we continue on with the first plenary session, we would like to invite all participants and esteemed guests to take a few official photos together. My colleague will take a screenshot of each participant page from Zoom. For those of you currently setting your video off, please turn on your video for the photo session. Okay, ladies and gentlemen, are you ready? The first page, we're going to take a picture from the first page. Mas Gunawan, 1, 2, and 3. Now the second page. Mas Gunawan, ready? Everybody turn on your camera. 1, 2, and 3. And the last page. Please turn on your camera, everyone. 1, 2, and 3. Thank you. Ladies and gentlemen, the first plenary session of the International Symposium on Biomedical Engineering 2021 will now begin. Before we begin the plenary session, please allow me to inform you of a few rules to help make the session run smoothly. Please make sure that you have adjusted your username in accordance with the name used for registration. Please make sure that your microphone is set to mute during both the plenary sessions. If you need any assistance during the session, please use the chat room to inform the committee. For the question and answer, the moderator will direct on how the question should be asked. If you're interested in further discussion with any of our keynote speakers, we will later on set up breakout rooms, and please contact the committee through the chat room for further assistance. Ladies and gentlemen, our first plenary session will feature talks from Professor Chao-Ling Yao from Yunzi University, Taiwan, and Dr. Alan Tan from Dassault Systems Private Limited, Singapore. The first plenary session will be moderated by Associate Professor Muhammad Hussein Ismail from the College of Engineering, Universiti Teknologi MARA, Malaysia. Please allow me to read a brief profile of the moderator before I transfer the screen to him. Associate Professor Muhammad Hussein Ismail received his Master of Science degree in Mechanical and Materials Engineering from Universiti Kebangsaan Malaysia in 2002 and his PhD degree in Engineering Materials from Sheffield University, United Kingdom in 2013. He joined Universiti Teknologi MARA as a lecturer in 2001. Currently, he serves as the head of Linkage, School of Engineering, Universiti Teknologi MARA, and his research interests are industrial metallurgy, materials, characterization, powder metallurgy, particularly metal injection molding, shape memory and ITI alloy, porous biometallic or ceramic, and metallic foam. He has published 3 book chapters, 50 referred journals, and more than 50 conference proceedings, both international and local. He has 3 patents and 1 utility innovation. Dr. Ismail, the session is now yours.
Okay, thanks, Tika, for the kind introduction. Ladies and gentlemen, may I have your attention? The presentation is about to begin. Our honorable guest, Pak Yudan, Dean of Faculty of Engineering, Assistant Vice Chancellor, Dr. Professor IR Insigne, Surveyor, Prof. Suhaimi, our honorable keynote speaker for this morning's session, Prof. Chao-Ling Yao from Yunzi University, Taiwan, and Dr. Alan Tan from Dassault Systems Limited, Singapore. Distinguished guests of ISBE 2021, ladies and gentlemen. Assalamualaikum warahmatullahi wabarakatuh, and a very good morning. First of all, I would like to welcome you to this keynote session 1. Our first keynote speaker is Prof. Chao-Ling Yao from Yunzi University, Taiwan. His presentation title is Expansions and Differentiation of Cord Blood Hematopoietic Stem Cell Therapy and Immunotherapy. Before the presentation begins, allow me to introduce our first keynote speaker. Prof. Chao-Ling Yao is a professor in Department of Chemical Engineering, and Material Science, and in the Graduate School of Biotechnology and Bioengineering at Yunzi University. Currently, he is a General Secretary in Taiwan Genetic Testing and Stem Cell Research and Development Association and Committee of Institutional Review Board of Taoyuan General Hospital, Ministry of Health and Welfare, Taiwan. He received LCY Foundation Outstanding Research Young Professor Award in 2019, the Award of Excellence in Research in 2017, and several times got Young Scholar Research Award. His research interest is hematopoietic stem cell research. He also has many publications in journals related to his field. To welcome Prof. Chow Ling Yeo to deliver his presentation.
Good morning, Chairman, ladies and gentlemen. First of all, I would like to thank the organizing committee of ISBE 2021 and the president of AFOB, Professor Wen-Chen Li. It's my great honor to be invited here and serve as the keynote speaker for the ISBE 2021. Today, my talk topic is expansion and the differentiation of cord blood hematopoietic stem cell for cell therapy and immunotherapy. I'm Cao Ling Yao from the Yunzi University, Taiwan. The campus of Yunzi University is very beautiful. So after the COVID-19 pandemic, if you have the free time, welcome to Taiwan and visit the Yunzi University. Before my presentation, I would like to introduce the context in my lab. My lab focuses on the stem cell research, especially on the adult stem cell, including the hematopoietic stem cell, endothelial progenitor cell, liver stem cell, mesenchymal stroma cell, and the intestinal stem cell. You can find that the different types of adult stem cells show the different morphology under the microscopic observation. They are so beautiful and attractable. The major limitation of the stem cell for the clinical application is the cell number. The number harvested from the donor is usually not enough for transplantation. So the fourth cortex in my lab is to develop the serum-free and the chemical-defined ex vivo culture system for various types of adult stem cells to expand the stem cell number, to maintain the stem cell function, and to solve the cell number issue in clinical application. Today, my talk will focus on the hematopoietic stem cell. The second cortex in my lab is to develop the induction system for various types of adult stem cells. In my lab, we can induce the stem cell into specific types of mature cells. This induction system can play important role for cell therapy, immunotherapy, and humanized mice establishment. For example, we can induce the hematopoietic stem cell into a red blood cell to treat for anemia, or into the natural killer cell to fight with cancer. We also can induce the mesenchymal stroma cell into the bone or cartilage for tissue regeneration. In addition, we are trying to inject less expanded hematopoietic stem cell into immunodeficiency mice to generate humanized mice. Humanized mice means the mice contain human cells and can mimic human body environment. Hence, humanized mice are the powerful animal tool for new drug screening and new therapy development. The price of one humanized mice is $1,000 US. In the future, we can generate a large amount of humanized mice with low cost. Let's go down to the main rule of my talk, hematopoietic stem cell. This is outline. Firstly, I will introduce hematopoietic stem cell briefly. Then I will share the result of the serum-free expansion of hematopoietic stem cell. In the last part, I will share the result of induction of the serum-free expanded hematopoietic stem cell into the lymphoid lineage and the myeloid lineage. What is a hematopoietic stem cell? A hematopoietic stem cell is a cell isolated from the bone marrow or peripheral blood or cord blood that can renew itself and differentiate into the lymphoid and the myeloid lineage. This cartoon picture shows the differentiation ability of hematopoietic stem cell. We can harvest hematopoietic stem cell from the bone marrow, peripheral blood, or cord blood. Hematopoietic stem cell can differentiate into two pathways. The first one is the myeloid lineage, including the white blood cell, red blood cell, and the platelet. White blood cell, including the neutrophil, basophil, and eosinophil. And the megakaryocytes are the progenitor cell of the platelets. And in the other way is the lymphoid progenitor cell, including the natural killer cell, T lymphocyte, and the B lymphocyte. This is the immune system. Hematopoietic stem cells locate in the bone marrow, and it can mobilize out of the bone marrow into circulating blood, and it also can home from the circulating blood to bone marrow. These are the foundation of the hematopoietic stem cell transplantation in the clinical application. There are many surface markers are used to identify the hematopoietic stem cell, including the CD34, CD163, CXCR4, and the not expressed CD38. The surface marker CD34 and the CD38 are the most important indicators to identify the hematopoietic stem cell. This cartoon picture shows that the primitive hematopoietic stem cell highly express CD34 and not express CD38. When the hematopoietic stem cell differentiate into the mature cell, the CD34 express would decrease and the CD38 expression would increase. In clinic, hematopoietic stem cell have been used to treat many diseases over 50 years, such as the leukemia, lymphoma, inherent blood disorder, and solid tumor. If one patient has the above disease, he or she will be treated with high dose of chemotherapy and radiotherapy to destroy the wrong bone marrow function. Then the autologous hematopoietic stem cell or matched allogeneic hematopoietic stem cell will be transplanted into the patient and recover correct bone marrow function to generate all types of blood cell and immune cell. In my lab, we believe hematopoietic stem cell can do more things and play more role in clinics. So we developed one is vivo hematopoietic stem cell in vivo systems and several hematopoietic stem cell induction systems to induce hematopoietic stem cell into the natural killer cell or dendritic cell for immunotherapy, or induce into the platelet or red blood cell for cell therapy. And we can use this systems to serve as the cell-based screen platform to screen the drug or biological candidate. For the stem cell research and the cell immunotherapy, there are several limitations must be overcome, such as the limited cell availability, low stem cell number in one harvest unit. This means that the cell number is not enough. Other limitations are loss of the stemness and the difficult control of stem cell fat. So it is an important issue to develop its vivo expansion and induction system for hematopoietic stem cells. This system should have the ability to increase the hematopoietic stem cell number and have the ability to guide the hematopoietic stem cell into a specific type of the mature cell. Importantly, this system needs to comply with the clinical regulation, current CGTP and current GMP. How to expand the hematopoietic stem cell? Based on the literature recorded, several methods were used to expand hematopoietic stem cell in vitro. such as co-culture with animal-derived stromal cell, serine or plasma adhesion, and cytokine adhesion. However, the current CGTP recognition cannot permit the first two methods because the stem cell culture with stromal cell, serine or plasma will have the risk to be contaminated and cause serious immune response. The effects of the cytokine are complex. One cytokine may act on different types of cells and have different effects, depending on the target cell, its concentration, and the presence of other cytokines. So in my lab, we want to ask two questions. The first one is, can hematopoietic stem cell be expanded in vitro and in the serum-free and chemical-defined environment? And the second one is, can in vitro expanded hematopoietic stem cell maintain the full differentiation ability into various types of blood and immune cells? If the both answers are yes, that means that we have ability to solve the limitation of hematopoietic stem cell number for transplantation and engraftment, and to enhance the recovery after hematopoietic stem cell transplantation, and to serve as a promising cell source for cell therapy and application. In my lab, we use the mathematical and statistical method to screen serine substitutes and the cytokines that have the positive effect on hematopoietic stem cell expansion or differentiation, and optimize their combination and concentration. Due to the limitation of time, today I will give this part and only show the result. So in the beginning, if we only harvest a small amount of hematopoietic stem cell, we can expand the cell number under the serum-free and chemical-defined condition and get a large amount of hematopoietic stem cell with correct function for transplantation. In addition, we can thoroughly induce the expanded hematopoietic stem cell into various types of mature cell or immune cell for cell therapy and immunotherapy. Now let's go to see the result of the first part in my study, stem cell expansion under the serum-free condition. In my lab, the first chemical defined and clinical grade expansion system was developed for the hematopoietic stem cell. It is called a serum-free hematopoietic stem cell expansion medium. This system contains one backbone medium, 7 cytokines, and 4 serine substitutes. We have published this result in several SCI papers and got the US patent. Our results demonstrate that after a 7-day batch culture in the serum-free HSC medium, the hematopoietic stem cell number can be expanded up to the 34th, and the cell cycle distribution is similar with the freshly isolated hematopoietic stem cell. In addition, if we change the median every week, the hematopoietic stem cell number can continue to expand up to the 1 million fold. After 7 days batch culture, we also check the surface marker expression of expanded hematopoietic stem cell. Our results show that most expanded hematopoietic stem cell highly express the CD34, CD133, and not express CD38. That means the most expanded cells in our system are the primitive hematopoietic stem cell. Importantly, compared with the freshly isolated hematopoietic stem cell, the number of the primitive hematopoietic stem cell can expand approximately over 600-fold. In addition to the surface marker analysis, the functional assay of the expanded hematopoietic stem cell are also checked. currently forming cell assays and the long-term culture initiating cell assays group. All results show that the expanded hematopoietic stem cell also maintain the ability to form the various types of hematopoietic colony, such as the BFUEs with the high frequency, and also maintain ability for the long-term proliferation. The primitive hematopoietic stem cell has the high ability to proliferate. So hematopoietic stem cell will express high activity of telomerase to maintain the telomere length in the end of the DNA after cell division. Hence, we check the telomerase and the telomere length of the expanded hematopoietic stem cell after 7 days culture in the serum-free HSC system. Our results show that the gene expression of the telomerase, H3, and the activity of the telomerase upregulate with the culture time. That means that the truly primitive hematopoietic stem cells are expanded in our system. In addition, the telomerase length was maintained at 30 kilobase. That is similar with the fresh isolated hematopoietic stem cells. Besides to the in vitro functional assay, in vivo assay of hematopoietic stem cell was also checked. The most important in vitro assay is the skin mice recapitulating cell assay, SRC assay, to check the ability of bone marrow recovery. We take the non-skin mice in this assay. We separate the mice into 4 groups. Group A is the normal healthy mice without treated. The mice in the group B, C, D were treated with 4-grade irradiation to destroy mice bone marrow function. Then inject the hematopoietic stem cell into the mice via the tail vein to check the cell ability to recover the mice bone marrow function. All results show that the mice in group D with 4-grade irradiation and without hematopoietic stem cell transplantation will die within 2 weeks due to the hematopoietic failure. The bone marrow environment is empty and cannot find any cell. Group B and Group C are irradiated mice with the fresh isolated hematopoietic stem cell and expanded hematopoietic stem cell transplantation respectively. The mice in this group has both the high survival rate and continue to survive up to 2 months, even up to 1 year. After 1 week, we sacrifice the mice and check the bone marrow. Their bone marrow environments are similar with the normal healthy mice in the group A and are full of the hematopoietic stem cell. In addition, we harvest the cell from the bone marrow and check the surface marker. We can find high percentage of human hematopoietic stem cell in the mice, bone marrow in group B and group C, and the frequency are similar in these 2 groups. This result indicates that the expanded hematopoietic stem cells show a similar ability with the fresh isolated hematopoietic stem cell to recover the bone marrow function and save the life of mice. Taken together, our results demonstrate that hematopoietic stem cell can be expanded efficiently in the serum-free HSC system and maintain all the property and the function. Since we can expand hematopoietic stem cell and get a large amount of hematopoietic stem cell, then we try to develop the induction system to induce the expanded hematopoietic stem cell into specific mature cell or immune cell for cell therapy and immune therapy. For the lymphoid lineage, we developed a serum-free natural killer cell induction system to induce the expanded hematopoietic stem cell into the natural killer cell for immunotherapy. What is a natural killer cell? Natural killer cells are large granule lymphocytes in the peripheral blood. 10 to 50% lymphocytes are natural killer cells. Natural killer cells express CD56 and not express CD3. Natural killer cells play important role in the innate immunity and can attack cancer and the tumor cell without the presence of antigen-presenting cell. In my lab, we succeed to develop natural killer induction system that can induce the expanded hematopoietic stem cell specifically into the natural killer cell. After 6-week induction, the CD56 positive and the CD3 negative natural killer cells are highly induced. In order to mass production of natural killer cells, we combine the serum-free HSC expansion system and the natural killer cell induction system to track the natural killer cell generation. It is the struct 1. In the struct 1, we can generate large amount of natural killer cells with high cell purity, approximate to the 16 to 70%. After calculation, one fresh isolated hematopoietic stem cell can generate 30 expanded hematopoietic stem cells, and one expanded hematopoietic stem cell can generate 320 natural killer cells. That means one fresh isolated hematopoietic stem cell can generate 9,600 natural killer cells. It is a promising cell source for the immunotherapy. We check the in vitro functional assay of the induced natural killer cell in our lab. Our results demonstrate that the induced natural killer cells exhibit higher ability to secrete interferon gamma and show more powerful ability to against cancer cell in vitro than the orange one. Importantly, we also check the in vivo functional assay of the induced natural killer cell. In this assay, we take the non-skin mice and separate them into 2 groups. The mice in the group 1 are injected with cancer cell only, and group 2 are injected the cancer cell and induced natural killer cell at the same time. After 4 weeks, we can find that the tumor size in the group 1 is large, and the average tumor area is around 240 millimeters square. However, the tumor size in the group 2 are reduced significantly, and the area is around 24 millimeters square, only 1/10 of the group 1. This means that the induced natural killer cell in our lab show more powerful ability to against tumor than orange cell and have the potential to use for immunotherapy. The last case is for the myeloid lineage differentiation. In this study, we developed a serum-free megakaryocyte induction medium to induce the expanded hematopoietic stem cell into megakaryocyte for cell therapy. What is the megakaryocyte? In the peripheral blood, 1% myeloid cells are megakaryocyte. Megakaryocyte will carry out the endomitosis and cytoplasmic maturation to perform the polyploidy. Megakaryocytes express CD41A and CD61. Megakaryocyte also called platelet progenitor. One megakaryocyte can generate 2,000 to 5,000 platelets when they go through the microvessel. Megakaryocyte play important role in hemostasis, and thrombosis, and can be used to treat the thrombocytopenia. In my lab, we succeeded to develop megakaryocyte induction system that can induce the expanded hematopoietic stem cell specifically into the megakaryocyte. After 1 week induction, the CD41A positive and the CD61 megakaryocytes are highly induced. In order to mass production of megakaryocytes, we also combine the hematopoietic stem cell expansion system and the megakaryocyte induction system to check the megakaryocyte generation. In step 1, we can generate large amount of megakaryocytes with high cell purity. After calculation, one expanded hematopoietic stem cell can generate around 5,000 megakaryocytes. That means one fresh isolated hematopoietic stem cell can generate 150,000 of megakaryocytes. It is a promising cell dose for cell therapy. We check the in vitro functional assay of the induced megakaryocyte in our lab. Our results demonstrate that the induced megakaryocyte express NFE2 and DATA1. These are important transcription factors during the megakaryocyte process. After stimulation with the collagen, the induced megakaryocyte will highly express CD62P. That means these megakaryocytes maintain the ability and are ready to become the platelet. In addition, the induced megakaryocytes show polypority and can form the megakaryocyte colony. These are represent the induced megakaryocyte have the correct function. Importantly, we also check the in vivo functional assay of induced megakaryocyte. In this study, we take the non-skin mice and separate them into 4 groups. Here, you only need to focus on the group 2 and group 4. Group 2 is the mice with the irradiation and the transplantation with the expanded hematopoietic stem cell only. Group 4 is the mice with the irradiation and the transplantation with the expanded hematopoietic stem cell and the induced megakaryocyte. After transplantation, the distribution of human platelet in the peripheral blood and the human megakaryocyte in the bone marrow will be analyzed at the indicated time point to check the platelet recovery. Our results show that after transplantation, the concentration of human platelet in mouse peripheral blood will increase with the time. And the group 4 show the highest human platelet distribution. After 2 weeks of transplantation, the mice were sacrificed and the cells in the bone marrow were harvested to analyze. We find that the bone marrow contains the highest amount of human megakaryocyte in group 4, okay, CD61 positive cell. Taken together, our results demonstrate that the induced megakaryocyte in our lab had the ability to generate platelets and had the potential to use for cell therapy. Here, I make a brief summary. In my lab, a stroma-free, scene-free, chemical-defined, and cytokine-optimized medium, C3 HSC medium has been developed for expansion of hematopoietic stem cells. C3 expanded cells satisfy both in vitro and in vivo criteria for hematopoietic stem cells. For example, correct surface marker extraction, long-term cultural ability, and multiple differentiation potential, home ability, in vitro environment ability, and the telomerase activity. Serum-free expanded hematopoietin cell retain their hematopoietic multipotency to differentiate into the functional natural killer cell and the megakaryocyte, and can be used for the immunotherapy and the cell therapy. The induced natural killer cell were confirmed by their characteristic and functional analysis. For example, surface marker interferon gamma secretion, cytotoxicity, and in vivo start. And for the megakaryocyte were also confirmed by their characteristic and functional analysis. For example, correct surface marker expression, priority distribution, platelet activation, NFE2 and GATA1 expression, and in vivo starting. Finally, whole process of serum-free and chemical-defined expansion and induction for mature blood cell generation can provide a promising cell source for immunotherapy and cell therapy in the future. The above research work are difficult and tough. I cannot do it alone. I want to thank my partner and the students left here. Finally, thank you for your attention and listening.
Thank you very much, Prof, for the informative and interesting talk. Ladies and gentlemen, next we proceed to the second keynote speaker. Our second keynote speaker is Dr. Alan Tan from Dassault System Pte Limited, Singapore. His presentation title is Virtual Human Modeling. For those who have a question for the session one, please kindly write your question through a chat box, and we'll be discuss the question through during the discussion session after the end of keynote 2. Right, a little bit background of Dr. Alan. Dr. Alan is a Simulia sales director for AP South and is responsible for sales management of the Simulia products. Prior to this role, he was also the technical leader for Simulia in AP South. Alan joined DS Japan in 2009 as a pre-sales consultant, progressing to fatigue lead in Asia Pacific. He worked on different industries in Japan, including life sciences, where he advised clients on analysis and fatigue. Prior to DS, Dassault System, Alan worked in Japanese consulting company responsible for structural and geotechnical analysis. He also worked as postdoctoral researchers for Tokyo Institute of Technology under the Center of Urban Earthquake Engineering. Before Japan, he was a member of the faculty in the University of Philippines, teaching solid mechanics, advanced engineering, mathematics, and design of concrete and steel structures. He holds a doctorate from the Department of Civil Engineering, Tokyo Institute of Technology, and his master and bachelor degrees in civil engineering from University of Philippines, Diliman. Without further ado, I would like to welcome Dr. Alan to deliver his presentation. Dr. Alan, the screen is yours.
Hello everyone, and let me share my screen first. I hope you can hear me properly. Okay. So thank you, Muhammad, for the kind introduction. I'll start presenting. Okay. So, my presentation is on the virtual human modeling. Just for introduction, AP South means Asia Pacific South, which includes ASEAN countries and New Zealand, right? Australia and New Zealand. So we do a lot of simulation in our industry, and we sell software for simulation. Okay. For corporate introduction, okay. So our company is what we call a purpose-driven company, right? We look at creating value for the planet, and we wanted to harmonize product, nature, and life. So there's around 20,000 passionate people in our company. Okay. and maybe a lot of nationalities as well. We have a lot of this, and we have R&Ds around the world. Okay, we have partners who sell our software as well. And we have the most important one is we have a lot of customers using our product in the 11 industries worldwide. Okay, so the profound belief that the virtual world extends and improves the natural world. So that's our belief. We wanted to use the virtual world. So in life, okay, there's no rehearsal. Okay, you cannot die and come back to life, right? You cannot destroy something and do it again. But in simulation, you can evaluate the impact, the changes before going to actual life, right? So by this, we inspire and help customers create and build a more sustainable world, right, for cities, people, and to manage the resources. Okay, so our purpose in the company, okay, is to provide business and people with 3D experience universes to imagine sustainable innovation. So we need sustainable innovation to capable of harmonizing product, nature, and life. So that's our purpose. And the legacy we have, people ask us, what are we, right? So it started in 1981. Okay, we call it the 3D design. So you design a small part. Then in 1989, it became the whole airplane itself, the digital mock-up. Then 1999, where we started the life cycle management. You look at the product life cycle. And as we continue, we found out that we need to innovate more. So then the next stage is where we call the fourth stage is where we have the 3D experience, okay, where you have perception and emotion to represent everything. So we transform everything. Like in this example, the city of Singapore was in the whole platform. Okay, the whole everything is there. And again, in the near future or in the current stage, is the representation of things to life. Okay, so the human body, the virtual twin of human experiences. So that's where we are now, and we are continuing to develop. And what is Simulia for life sciences? Okay, so modeling and simulation plays a key role in pharma and biotech. Okay, in our simulation tools are mostly used for chemistry and biology, for medical devices. Okay, and then in medical devices, there a culture of simulation usage, but not as much as most of our industries. Okay, but lately we see a lot of what you call patient care is coming, right? So patient care is becoming the impact or simulation usage as well. Okay, so our aim is to combine all of this to be able to use them in patient care. Okay, and to bring all these areas to human healthcare. So when you do that, you need the tools. So what do we have? We have the multi-physics solution in the left, right? So you have structures, fluids, electromagnetics, multi-body and system modeling. Once you do the multi-physics, you can look at durability and life, how long it takes before damage occurs, and you look at optimization, control of the processes, right? You can look at different iterations. But the key factor here is to have the human or the virtual human modeling, which we have in our platform. Okay. So that's where we are looking at. We want to look at extensive experience in modeling the realistic physical behavior products, okay, and interacting with the human body. Okay, that's where we are. Okay, and this is where the human virtual modeling or virtual human modeling is. So we look at internal body systems and organs. Okay, it could be the brain function, eye and vision, cardiovascular is very common now, skin and aging, printed parts, right? We put printed parts as well, and orthopedics. But at the same time, why do we want virtual human modeling? Is for to have the interaction with the environment. Okay, we need to interact with the environment as well. Okay, so you can see here motion, the fluid flow. Okay, we have cars, we have the wearables. You have some clients develop clothes, right, with human interaction. Okay, and mechanics, the movement, and electromagnetics. Okay, so as we continue, what are the virtual human modeling? We started with the living heart model. Okay, And this will be very important even for the researchers out there, that you can use our model to look at developing things around the human heart or just learning about the heart itself. So it started with the geometry, where we have the MRI and CT scans. Okay, images are done. Then you look at the tissues, the tissue of the heart itself. So modeling tissue is important. It's not as simple you pull and it's like steel, right? It's not like that. So it has a direction, orthotrophic direction, right? So these were created. So again, by having these two, the living heart or the living human heart model is created from segmenting a normally healthy heart for medical images, right? We do a normal healthy heart and define the interactive tissue, the passive and active, as constitutive behavior. We added the myocardium fiber orientation, and we added the electrical and mechanical physics. Okay, with then the valves are included, the fluid cavity is included as well. Okay, and from that we have the beating 4-chambered heart. That's where we started the building the living heart. Okay, and why do we do this? Okay, you can see the coupled physics here. Okay, electrical results, and the Purkinje network is called Purkinje network is added. Okay, it's where you have the fibers in there is added there as well. Okay, it to drive the electrical simulation, or to have the electrical stimulation to drive the mechanical contraction. So once you have the electrical stimulation, you can have it contract. You can see here the heart is contracting. Okay, you have the motion. If you remove the ventricles, you just remove it or hide it. Okay, I should say it's hidden. Then you can see the movement as well as the mitral valve. So here, the mechanical deformation, okay, is shown here with structures like coronaries and the 4 valves, right? Okay, and again, in the clinical view of the sample, so we look at the realistically rendered. So this is a rendered image from the previous result. So we realistically rendered it so that you can communicate with project stakeholders. So not everybody knows simulation, but they know that the heart is moving. So you can discuss, right? How simulation, what happens, how it moves. You can even perceive the heart's motion if you want, right? You look at the electrical signals, you can remove parts and see what's happening inside. Okay, so that's a clinical view that we have. And you can slice through, as I've said, look at what's inside. And when we started the living heart modeling framework, right? So our living heart project. So we look at the framework, and the foundation is a multi-scale. The technology is the foundation, the multi-scale, multi-physics. Okay, but around those, we continued building the extension. Okay, on the core technologies like developing the constitutive laws for the heart tissue, right? To capture the active and passive response. And from there, of course, not only that, we need the models to create the heart-to-heart. Okay, the DS, they create the models with a lot of collaborators in the industry. Okay, so we have joint collaboration with universities in the US, with clients in the US, looking at sharing the model, right? Then we make it accessible, shareable, and customizable. So you can change the heart, the geometry if you want. You can change the material properties. Okay, so that's where we wanted it to be, and that's where the Living Heart project is. So you can choose to join us, or you can purchase the software and be able to use the heart model itself, right? So why are we doing this? The application is vast. So the members of the project have actually used the heart to virtually test a full range of cardiovascular products already. Okay, so they can study heart disease on the left, right? They started looking at, okay, what's the heart disease? What changes in the material properties? If you drink medicine, you can change the elasticity of the heart. What happens, right? So they can change the treatment, understanding what's happening inside the heart. including the electrical system, the tissue mechanics, and blood flow. So that's a very big step forward. Okay, and the next is the ability to assess the device function inside the heart. So you create pacemakers, stents, valves, left valve, and devices, right? But you can create this, but what happens inside the heart is unknown if you create it separately. So then, by having the living heart or human heart, living heart application, you put it in the heart, and you can see how you can develop this further. Okay. So again, we are not yet on the point of actual virtual clinical trials, but this is a big progress, right? That you can use this for clinical trials in the future. Okay. So again, it could be pacemaker. A lot of this are developed. Okay, and you can examine valve replacement as well, right? Okay, so that's the model is developed, right? So it's now used by over 100 members in the Living Heart Project community, okay, where it helps us make it better. The development is better, right? So you can see here it's been used for the virtual clinical trials, medical device design, okay, the patients as well for human heart disease or people heart disease and virtual patients. 3D printing if you have personalized organs, machine learning and AI, they can use our virtual tool to train the machine learning or train their machines. It could be drug safety and medical images. So again, in the framework of the Living Heart project that we had, okay, we look at the verification. That's the first one. Okay, if the simulation results solve the mathematical models. Category 1 is Category 1 is agreement between generally expected behavior. Category 2 is calibration. Category 3 is general validation. Okay, with agreement of the no specific COU or context of use. And category 3, again, the next part of category 3 is looking at the context of use. Okay, so that's where we are. So looking at category 1, you can see that it has expected agreement with published normal research as well. Okay, with a healthy male. So some might not be exactly, but because again, healthy human male and could be a bit different. Okay, that's where we need to add more development, but now it's consistent actually being used. Category 3 is calibration. You calibrate the electrical activation. Initially, it was calibrated with activation times only, but by adding complexity, looking at the base and apex, even the movement, then it changed calibration. Then it was better calibrated now, okay, to achieve the base to apex and through the ventricle free walls. Okay. And again, as done by Microport, our client, they look at calibrating it as well on the septum to free walls, anterior to posterior as well. So they need to make corrections to the Purkinje network to refine the model better. Okay, and continuing with Dr. Kasu's model, okay, comparison between against patient data for left ventricle endocardium as well. Okay, it's completed model with an actual patient. Okay, red represents the wave front, the wave passing through, right? Okay, general, the category 3 is the general validation of virtual and real. So the left is a virtual. It looks real though, but again, it is virtual with different thicknesses. Okay. And this was done by the University College of London. Okay, showing all of this. Just to show the comparison and good agreement, not on the movement as well. And you can see the exhibition of wall thickening, circumferential and longitudinal shortening as well. And the twisting on contraction, you can see it contracts. It twists a little bit on some sides, right? So the walls are thickening or thinning in some areas. Okay, you can see here that's how it looks. Okay, with actual comparison on the images, not only on time, the movement, but how it looks. Okay. In category 3, we our partner Exponent did 3 successive studies on comparison in vivo. Okay, so looking at what type of loading. So they found out it's a conservative loading condition, so it's safe if you do it. So motions on the left anterior descending artery there, you can see the systole and diastole. So the FEA loading as well in comparison with in vivo measurements. Okay, and they continued on working on that as well on the case studies. Okay. The next one that we are looking into is the musculoskeletal model. Okay, so this again an example of another human modeling that we have. So this is a knee replacement surgery. So again, if you look at knee replacement, this is a YouTube video. You can see the causes is, it could be osteoarthritis, rheumatoid arthritis, or any post-traumatic arthritis. So that's a movement. But so this is very common procedure now. So we can see the potential by adding the tool, right? So here you can see the reconstructed 3D knee analysis. So if you have the digital knee twin or the human heart twin, right, you can create a digital knee twin. So you can look at ligament tension, dynamic motion here as well, right? So you can see lateral movement here. Okay. A pre-surgical knee analysis, you see what's happening, why it's moving, what's with the femur and without the femur, right? You can see the interrogation or the knee motion. Okay, you can see the complete picture of the patient condition. Okay, and the motion capture if they walk, the gait itself. Okay, you can replace the avatar of the patient and capture what's happening in his knee and looking at the specific motion. Okay, and what precise reproduction of the patient's mobility, right, is created, or what do we need to evaluate forces and everything, and how do we, what's the best for surgery. Okay, so that's the patient specific gait. Okay, you can see here we did a visualization and the tools, right? You can see the augmented reality. Okay, I hope that looks good. And these models can also be visualized like that. But for a surgeon, you can look at it as we have also a 3D model using AR tablet to enable 3D, right? You can do it in 3D. You can see, okay, what should I change? What you can practice surgery as well, okay, at the same time with the actual knee patient. So the twin can be done. Okay, and in this case, the ligament forces differ due to misalignment during rotation. So you can see where it's misaligned as well. And here you can see increased force due to pain, leads to pain and wear, right? So because of the increased forces here. Okay, so that's the misaligned, the aligned is better, you can see here. And because of that, you can lead to the, help you look at the pain as well. And after the post-surgical gait analysis, you evaluate the plan as well on if you change this, what happens, right? And this is before and after the total knee replacement, same person, right? But different, looks different. Okay, and of course, I say there's further examples of virtual human modeling, but at the same time, there are further examples also of what you say simulation in the life science industry. So we could look at the biomedical product packaging. It could be pre-filled syringes, drug delivery devices, and delivery packaging. Okay, you can develop this as part. You can also use the virtual medical device testing. So here you can see the physical and virtual tests. Okay, this is a stent to look at what's happening on that. And at the right is the syringe, right? Some of our researchers done the head impact modeling and what happens to the brain using the head model. So this is an impact for NFL helmets, right? Cricket helmets is the company, I think. Okay, so in this example, the Naval Research Laboratory in the US did a lot of study on the head impact, okay, for potential to head injury. We could also look at drug delivery device designed for in a virtual human modeling. You can add it, okay, when you deliver drugs. Okay, you could look at drug eluting stents where you put drugs in the stent as well. Okay, so in this case, you look at the whole stent, you crimp it, you insert it in the guide wire, you put it in the heart, inside the heart. Here you can see here. Okay, and you balloon it, or if it's nitinol, it increases it by itself. You expand it, and you look at the pulsatile pressure, and then you can see the vectors. Okay, what happens on the volume of drug that you can release. Okay. So again, that's another example of a human heart model. Another one is the syringe, okay, pre-filled syringes, and then you need to model the tissue, okay, needle penetration. You can see here the experimentally simulated needle displacement. Okay. And again, this is coupled, you can couple it in a virtual human skin model. Okay, if you have the skin in different parts, you can choose where is the best location to inject, right? It could be drug skin interaction. If you have a drug that it diffuses in the tissue layer like this one, you can see here, right? Expansion. So that's for drug diffusion. But aside from this, where do I see the future of the virtual human modeling is actually including the consumer healthcare. Okay, a lot of this personalized health and wellness monitoring, it's been common now. You have your Apple, right, watches. Monitoring everybody now is the name of the game, right? But at the same time, you might want to look at, okay, the electrical fields, mechanical responses, and everything here as well. And additional discussion, you can see that in the human modeling, we need to have the right choice of biological model. So to be able to make this reliable, and the researchers could add a lot in our modeling, right? So for example, here we have available data for activities of daily living for 3 females and 3 males with 25 activities like sitting down, squatting, right? Motion, like deadlifting, actually picking out something on the floor, right? And we have tissue databases as well, reviewed. We have reviewed 226 papers. We have 12 tissue types, ligaments, skin, muscle, and bones, right? We also have the experimental data, brown experimental data with pinching, peeling, penetration, and everything. It could be the skin, fat, muscle, bone, and stomach. Okay. The detailed bone kinematics and the CST biomodel. CST is one of our tool for the electromagnetics. So you can see the electromagnetic effects, then how it changes the mechanical. So it's a co-simulation in between electromagnetic and mechanical. Okay. So again, those are the available data we have. Okay. And again, increasing the human body representation is important. Okay, so our virtual human modeling library is growing with kinematic models of the shoulders, hands, and legs. And you can see here. Okay. Already one of our major sports shoe manufacturers is looking at the athletic specific footwear design. So using data taken from MRI or CT scans of an athlete along with the gait. So when you walk, okay, to optimize the shoe based on the sports and based on the design on the foot and footwear, right? So you can see here a lot of future for the life science research as well. Okay. And again, as I've said, the next phase that we see is always patient specific models. So you specify the patient, you know the patient, you personalize decisions based on the patient. So it's not only this is the stent for everybody. So it's now based on this patient. So because of this, we can do, because of simulation and virtual human modeling, okay, the imaging to simulation to personalized decision is becoming the future. It's becoming really coming soon, or it's already here in many cases. So it could be the impact testing. You can have virtual implant testing. You can load patient-specific data to change values, right? You can forecast bone remodeling. You can also use additive manufacturing. You print out, now 3D printing is also very famous. So you can print out manufacturing designs and put it in the model of the person. So here you can see, to support the bone, right? It's a weakness of bone, you put something in there to replace it. Okay, then you can model the bone itself. Okay, and of course the real world data, you ask somebody to do the squats, if they can do squats, run gaits, right? And you can look at real world loads and predict remodeling over time, what happens, right? How does the structure? So again, what I see is the clinical environment is becoming digital. So today it's like this, but in the future, again, tomorrow, or even early in the near future, okay, it's becoming like that. So the clinical environment is changing rapidly, and Dassault system is helping to shape the way that change is occurring. Okay, we are helping to advance the life science industry, and you guys are helping us, okay, by introducing more research based on the simulation. Okay, and just to announce, for tomorrow there will be an Abacus workshop. Abacus is our structural tool, right? So you can try it out. I think Worley is included in the session. They will provide the Abacus workshop for tomorrow, okay, at 8:30 a.m. for Western Indonesian time. And that's my presentation. And thank you for listening to my talk.
Thank you very much, Dr. Allen, for the informative and interesting talk. Let's give him a big round of applause to
Mohammed, I think we lost you.
Hello?
Yeah, and now I can hear you. I think we lost you for a few minutes.
All right. Okay. Right. So now we are in discussion. Sorry. Right. From Retno Wahyu, thank you, Prof. Yao, for your great sharing. I am Retno from UI. I have a question. Do you get the similar expansion yield when using HSC isolated from BM or PB? And question number 2, one of the major challenge for ex vivo platelet production is to get similar platelet yield, hundreds platelets per megakaryote, with those platelet biogenesis in our body. How is your lab strategy to improve the platelet yield ex vivo? Thank you in advance. Prof. Chow?
Okay, thank you, Professor Ismail. Okay, for the first question, do you get the similar expression yet when using HSC isolated from bone marrow or peripheral blood? The answer is yes. We have cooperated with the hospital, okay, to check the hematopoietic stem cell isolated from the bone marrow and the peripheral blood, and try to expand this cell under the serum-free and the chemical-defined medium. And the results show that the cell from the bone marrow, peripheral blood, and the cord blood can expand efficiently in our system. However, the stem cell from the cord blood, it can expand mostly. Okay, the number is largely compared to the peripheral blood and the bone marrow. We guess the reason is the hematopoietic stem cell from the cord blood is youngest cell. Okay, so it has the most capacity to proliferation, so it can expand mostly in our system. But 3 cells from the bone marrow, peripheral blood, and cord blood can work in our system. That is for the first question. And for the second one of the major challenges for ex vivo platelet production is to get similar platelet yield, 100 platelets per megakaryocyte. With those platelet biogenesis in our body, how is your lab strategy to improve the platelet yield ex vivo? Okay, in this study, we only finished the animal transplantation, and you can see the result in the animal study. We can generate many human platelets, okay, in the mouse peripheral blood. So in the future, we will try to work with the hospital and to apply the IRB and to test the human clinical application. And in the other way, we also check the ability to lysis the megakaryocyte to form a platelet in vitro. And we found that 1 megakaryocyte can generate 2,000 to 5,000 platelets in vitro, okay, in our lab. So we hope in the future we can use this model to the human body. Okay, but we need to test. Okay, thank you.
Thank you, Prof. Chow, for the answers. Now we move to the second question by Khalifa. Dear Dr. Allen, very interesting. What does couple multiphysics means? And does the software provide also the case study of heart as you presented today?
Yes, I mean, just to answer, thank you, Khalifa. So the multiphysics, coupled multiphysics. So when we call multiphysics, you have the fluids, you have the structure, or chaplet physics, and you have the electromagnetic. When you say couple, you combine them so that the change in the electromagnetic will change or will stimulate or change mechanical structure as well. So it will move. So the fluid will also change, right? So you push water in, the structure will move somehow. So that's coupling between those multiphysics. And the second one, yes, it includes the heart. The model is included. So it's a special human modeling we call living heart. And the heart is included as well.
Thank you, Dr. Allen. And then we have another question from Dr. Sugeng. Dear Dr. Allen, thank you for your interesting presentation. Please explain hardware to run the complex simulation as shown in the presentation. Second question, is it possible to simulate blood cell motion? Thank you.
Okay, that's a bit, okay. First, the simulation, yes, it's not very special hardware now, especially we have fast computers. So I would say just a normal desktop will do, like 16 cores, 32 cores is common, right? So that's already being done. For the second question, the blood cell motion is a bit difficult topic to discuss because you need to look at the cell itself. I would say I've seen this sometimes with what we call the particle analysis. So yes, we do have particle, we call it the lattice Boltzmann method, or in the fluid. So we can put particle tracking there. Again, this could be a research.
All right, thank you. And then we have another question from participant Basari to Dr. Allen. What kind of method that simulators use for predicting the evaluating the model? It seems like finite element method or maybe FDTD or any other techniques. And question number 2, for human model, can we model by ourselves or it's already been available by Simulia and separate add-on product?
Okay, so for the first question, we use finite element method, okay, in terms of structure. For the electromagnetic, it's a combination of finite element or FDTT also. It's also there, right? Then for the other techniques, it's also finite volume is also included for the fluids, or lattice Boltzmann. So we have different methods. Okay. And for the human models, it's a separate add-on product. It's a different product. Of course, you can, if you have the geometry model, you can import it in Abacus as well. But yes, we have a specific tool called Living Hard. So it's a different platform.
All right. Thank you, Dr. Allen. And I believe that this will be another question from Dr. Yudan. Prof. Yao, is there any standard of your product?
I don't know what the means for the standard, but in Taiwan, we have a special regulation, okay, to open for the cell therapy and immunotherapy. Okay, so now we are trying hard to apply our result to fit the regulation. So we hope in the near future, we can use this expansion and induction system for the cell therapy and immunotherapy. But at the last, the standard for the cell therapy and the immunotherapy is the cell cannot contact with the external source component, such, for example, serum, animal serum or animal plasma. So in my lab, we try to develop the different types of culture system without the animal serum and without the plasma, and to fit the chemical defined criteria. That is the major issue in my lab. Okay.
Thank you, Prof. Yao.
Thank you.
Okay. I think, ladies and gentlemen, finally we come to the end of the part of keynote session 1. Thanks again. We'd like to thanks again to Prof. Yao and Dr. Allen for the very informative and interesting talk, and to audience for active participation. Thanks. Let's give him a big round of applause to Prof. Yao and Dr. Allen. Hopefully the presentation will be beneficial for everybody. For student participants, I humbly request you to fill up the attendance from the link provided through the chat box, and your kind cooperation is much appreciated. Thanks again. I would like to pass this session to Chairman for any announcement, or we go for the next session.
Thank you, Dr. Ismail. Ladies and gentlemen, as we have previously announced, breakout rooms are available for further in-depth discussion with both our keynote speakers from the first plenary session. Please contact the committee through chat room if you are interested in joining any of this room. We will now start the second plenary session of the International Symposium on Biomedical Engineering 2021. Please make sure that you have adjusted your username in accordance with the name used for registration. Please make sure that your microphone is set to mute during the plenary session. If you need any assistance during the session, please use the chat room to inform the committee. Question and answer will be directed by the moderator directly, so please wait for his instruction. For the second plenary session, we will have talks from Professor Kamaza Mulia from the Faculty of Engineering Universitas Indonesia, Dr. Rifai Chai from Swinburne University of Technology Australia, and Dr. Izhar Aziz, Managing Director of 3D Gens Sendirian Berhad. The second plenary session will be moderated by Associate Professor Yudan Wulanza, Director of Research Center for Biomedical Engineering Universitas Indonesia. Please allow me to read a brief profile of the moderator before I transfer the screen to him. Associate Professor Dr. Yudan Wulanza earned his bachelor degree in chemical engineering in 2000. After 2 years working in a company, he decided to study Master of Science at Aachen University, Germany, and started to join the Department of Mechanical Engineering Universitas Indonesia in 2006. In September 2008, he pursued his PhD program in bioengineering at Piaggio Research Center, University of Pisa, Italy, as part of European Union Asia Link program. He returned to Universitas Indonesia in January 2012 after the completion of his PhD program, and currently he serves as the Director of Research Center for Biomedical Engineering, Universitas Indonesia. He has published more than 70 journals and proceedings, and his research interests are biomimetics, biomaterials, biosensing, biomechanics, and locomotor tissue engineering. Dr. Yudan Wulanza, the session is now yours.
Thank you, Ms. Tika, for very kind introductions. And good morning, everyone. Assalamualaikum warahmatullahi wabarakatuh. It will be it's been honored from Dr. Zaki to give me this opportunity to host you through the second session. And we will have today the presentations from Professor Kamarza Mulya, entitled Green Extractions, Encapsulations, and Controlled Release of Drug or Bioactive Compounds. And shortly, his CV is that Prof. Kamarza received bachelor degree from the Bandung Institute of Technology in 1984, and then he continued with his master's science and also the doctoral in chemical engineering from the Colorado School of Mines, USA. At this moment, he served as professor in chemical engineering at Universitas Indonesia, and his research interests are extended and controlled release of bioactive compounds from biodegradable polymers, micro nanoparticles, improving health and diseases such as cancer, tuberculosis, and diabetic retinopathy, and also formulation for nutrition and health such as stability of iodine in iodized salts, also iron encapsulation to alleviate iron deficiency anemia. And he has proven to have funding from the Ministry of Research and also from the overseas, and he has many publications in journals or proceedings, especially in drug delivery. So let's give our moment to Prof. Kamarza Mulya. Prof. Kamarza, please, the time is yours.
Thank you very much, Dr. Yudan, for the kind introduction. I hope that you could see my presentation now.
Yes, we have.
All right, hold on a second, please. Yeah. First of all, I would like to say Assalamualaikum warahmatullahi wabarakatuh. Best wishes for everyone. And thank you for the organizing committee for giving me the chance to present a speech called Green Extraction, Encapsulation, and Controlled Release of Drugs or Bioactive Compounds. My name is Kamarza Mulya. I'm from Chemical Engineering Department. I'm also a member of the Research Center for Biomedical Engineering, Faculty of Engineering, Universitas Indonesia. All right. I would like to share with you some of the results from my research group. I would like to talk about starting with biodiversity, bioactive compounds, and then green extraction using a solvent called deep eutectic solvent or DES, followed by encapsulation, and then to have a controlled release system of bioactive compounds or drugs. And lastly, a little bit about multidisciplinary collaborative research. To talk about bioactive compounds up to drug delivery system is not possible in 2 hours. And I would like to say upfront that there are so many good research has been reported in journals, but let me just share the research that we have done in our research group simply because I'm more familiar with it. Okay, Indonesia is blessed with its biodiversity, and Indonesia has many medicinal plants, diverse and abundant, and then this medicinal plant can be used as sources for bioactive compounds. Now, the usual way to extract the bioactive compound is to use solvent extraction, and we usually use traditional organic solvents such as ethanol. Now, in this talk, I would like to, if you haven't heard about it, I would like to introduce you to deep eutectic solvent, which is known or regarded as green and designer solvent. Okay, let's say that we have a DES to extract bioactive compound and have the bioactive extract. Bioactive compound has many benefits to help us keep healthy or for medication, but as we can see here, many of them are unstable, toxic in high concentration, has low water solubility, and therefore low bioavailability. All right. At the end, you can see that we have encapsulating polymers. We use biodegradable and biocompatible polymers. And then with those polymers, we could encapsulate the bioactive compound so that we could minimize or eliminate the problem that I have mentioned just now. Okay, now after we have to encapsulate the extract, we have control the system, and we could optimize the system for application for health and medication. That's basically what I'm going to talk about in the next 25 minutes. Now we start with biodiversity. Indonesia has the second biggest biodiversity in the world. Well, from the literature that I read, it says that this country has around 25,000 to 30,000 plant species, but only about 300 plant species has been registered for medicinal use, and the remainder is used traditionally. Now we can see right away that there are ample opportunities for us to do research regarding bioactive compounds. It's free for everyone. Now, after talking about the limitation of bioactive compound, I would like to say that many kinds of bioactive compounds such as flavonoid, phenolic, isoflavone, carotenoid have significant activities. One or more is written here as antioxidant, anti-tumor, anti-inflammatory, anti-allergic, antibacterial, antifungal, and antiviral. Talking about COVID-19. Okay, we did an MTT test against breast cancer cell and find out that the IC50 values for mangostin and cisplatin is about the same order. Alpha-mangostin is a bioactive compound that extracted from the pericarp of mangostin. We call it manggis in Indonesia. And cisplatin is a commercial anti-cancer drug. And we also know that these drugs have common side effects. For example, nausea and vomiting, low blood counts, kidney toxicity, and blood test abnormalities. Now, these bioactive compounds, as you can see here, we can see from the molecular structure, we know right away that they have low solubility in water. For example, only around 90 ppm for alpha-mangostin. This low solubility in water leads to low bioavailability. For example, in Indonesia, we have jamu. So you just have a limited amount of bioactive compound present in the aqueous solution, or I could say in water. If we want to use these compounds for medical purposes, for example, to treat cancer, and then we need to have more concentrated formulations. And then we have to talk about higher extraction yields. And then that's where the use of green solvent is come. The second limitation of bioactive compound is its sensitivity to degradation because of light, water, heat, and acid. These two limitations could be eliminated if we encapsulate the bioactive compound to increase bioavailability and shelf life. Now we move on to deep eutectic solvent. What we see here is beta-in on the left interacting with two molecules of 1,3-propanediol. Now the beta-in is called HBA, hydrogen bonding acceptor, and the diol is called HBD, hydrogen bonding donor. These two opposite tendency with donating and withdrawing electron make them compatible to form hydrogen bonding. Now, water is a good solvent, and we know they have hydrogen bonding. This is like similar hydrogen bonding, but it's not water. It involves large molecules. Okay, so this hydrogen bonding enables this to solve solid molecules. And we could say that this is a mixture of HBA and one or more HBD, and not necessarily having a composition corresponding to the eutectic point. The eutectic point is shown here in the phase diagram, is the lowest melting point of the mixtures that could be achieved. Now, why people started to use this? Because they have low vapor pressure. When we use traditional solvent, they usually have a large tendency to evaporate, and then we produce a lot of huge amount of VOC, volatile organic compound. And traditionally, pharmaceutical industry has been blamed for introduction of a lot of VOC to the atmosphere. That's why DES after ionic liquid has been used. Now, if you choose HBA and SPD that are non-toxic and biodegradable, and you could say, okay, my DES is a green solvent. Now, another advantage of DES is that you could synthesize a large number of DES to be tested, because there are a large array of compounds or chemicals that you could select as an HBA or as an HBD. Hence, the word or the term designer solvent. Okay, I will start with the case number 1. We try to extract alpha mangosteen from the pericarp of mangosteen, fruit manggis, king of fruit. And I would like to emphasize here that we try to extract a good thing, a bioactive compound, from a waste, not the fruit itself, but the skin, the pericarp. So it has no monetary value, but we would like to get good things out of it. And here's the result. The plot shows the alpha mangosteen extraction yield, and that depends on the HBA and HBD use, and also the mole ratio of the two of them. And we can see, we compare with ethanol, they are about similar, but you only have limited selection of organic solvent. But in this, you practically have unlimited DES to be tested. Okay, now the data has been replotted as alpha mangosteen yield as a function of the NIRAD polar parameter. The lower the value of E and R, the more polar the solvent is. Now we could see some trend here, like hyperbolic or quadratic correlation, and we could see that the high performance DES has polarity close to that of ethanol. Now, especially in this case, I would like to say that the challenge is to recover the extracted bioactive compounds or the mangosteen. You see, if you have a very good solvent, and the solvent, of course, they would like to keep the solutes inside the solvent. That's why it's difficult. We have tried many ways to recover the bioactive compound, but still difficult. Okay, this is for case number 1. In the case number 2, the situation is reversed. This is the case where it is easy to recover the bioactive compound. Now, what is it? It is the acidification of palm oil. When you have palm oil, a fresh palm oil, it has certain percentage of palmitic acid. And this acid, when oxidized, tend to smell bad. It has rancid odor, and it lowers the quality of the palm oil. Now, we would like to use this to extract palmitic acid, but not to extract the nutraceuticals. We would like to leave the tocopherol and the carotene in the palm oil. Now, the present practice of the deacidification is steam stripping. Steam stripping at around 200 degrees C. That's a very high temperature. Now, the alternative is to use this extraction at 50 degrees C. Therefore, we could avoid nutraceutical thermal degradation and evaporation. And also, we haven't done the study on this, but we guess that we could reduce energy required to produce steam. There is no steam to be produced in this alternative process. Now, the way to do it is we mix palm oil that has palmitic acid and nutraceuticals with this in the extraction column. And after the equilibrium is reached, we transfer the mixture into the decantation tank and let the two liquids separate. That's on the top, and then we transfer it to the fractional freezer. There, the dish is cooled down a little bit, maybe to like around 20 degrees C, and we could have a solid palmitic acid as byproduct. The purified dish is returned back to the extraction column, while we have refined palm oil, including its nutraceutical, for further processing. Now the question is, would we find a dish that would do complete transfer of palmitic acid into this, complete retention of nutraceutical in palm oil, complete separation of solid palmitic acid, and keep this and palm oil mutually insoluble? If the answer to these four questions is a definite yes, then you could go to people in the plantation or in the palm oil industry and say, I have a better process than the steam stripping. The graph here shows the solubility of palmitic acid. And you can see we use butanediol to obtain diol. So long chain diols are more suitable to extract a C16 carboxylic acid, palmitic acid. And after we find the most promising dash, we check the distribution coefficients. The distribution coefficient for palmitic acid is good, but not excellent. It's 0.8. It's like saying about 20% of palmitic acid is still in the palm oil after one extraction. But for the nutraceuticals, the distribution coefficient is very good. It's already less than 0.01. Okay, now we have good things here, except the palmitic acid is still soluble in the palm oil. And for this certain dash, beta-in monohydrate and propionic acid, the IR and MLR spectra of the dash-rich phase, oil-rich phase, and the fresh palm oil indicates that propionic acid, the HBD of the dash, is partly soluble in the oil-rich or the raffinate phase. Now, as engineers, we know that it would lead to depletion of dash, and very soon you have to buy, purchase, or have new dash. That's not a sustained process. Fortunately, there's no indication that beta-in, the HBA, is transferred to the oil-rich phase. Now, this is the easy separation I talked before, that we could separate palmitic acid by simple cooling. If you wait for 12 hours, and then around 90% of the palmitic acid solidifies, and we could separate it, maybe sell it as byproduct. Now, if people ask how many times do you have to do the extraction, we could say 5 times. If we do 5 extraction equilibrium stages or 5 extraction equilibrium, and then we could reduce the amount of palmitic acid to the accepted level. Okay, now about the encapsulation. This slide shows that we could encapsulate the bioactive compound or drugs in so many forms. If you could see, maybe the word is not really readable. Nanoparticles, microparticles, beads, coating, films, liposomes, and so on. So you have so many opportunities, and drug delivery or controlled release system is very interesting subject to do research on, because then you have so many options to choose. You could be an expert in nanoemulsion and then also in nanoparticles and so on. Now, what are the benefits of controlled release or what are the benefits of encapsulating the drugs and the bioactive compound? First, we minimize bioactive degradation. That's important. And then also important, maintain constant level of bioactive in plasma to improve efficacy. Also, because we call drug delivery, we have targeted delivery, and all of this could lead to patient compliance. Okay. If you ask me, how do we do encapsulation? This is very simple. This particular experiment is very simple. You solubilize or you dissolve your drug in the in organic solvent, also the polymer, and then you pour or you mix the organic solvent into the continuous phase, which is water containing surfactant. You mix it, you then form micro emulsion or emulsion, such as this photograph, and then with time, the organic solvent will diffuse into water and then evaporates. And after the solubility concentration is surpassed, and then we will start to see solids. With this means that the polymer solidifies. And then in the end, we have dried microparticle or nanoparticles. Now, stopping here, if we can imagine, you could select a suitable polymer, and you could find drugs or bioactive compound that you would like to encapsulate, and then you can do many things with it. You can also have not in the form of the encapsulation product, and not in the form of microparticle, but could be in implant, films, you name it. And this is one of the example. Let's say that someone needs a hip replacement, and then to have that, he or she need to have, let's say, an alloy, cobalt chromium molybdenum alloy. And if our body knows that a foreign object is inside the body, and then it will react by inflammation. Okay. Now, it's not a good sign if one receives a hip replacement, and then there is inflammation in the nearby tissues. The way to avoid or to minimize the inflammation is to use dexamethasone, the anti-inflammatory drugs, and then encapsulate the drug into PLGA microparticles, and we disperse into the porous alloy, and then we can use supercritical CO2 to reduce the glass transition temperature of the polymer, and then the polymer will attach themselves to the surface of the inner pore. When the implant is used, the body fluid will be in contact with the polymers or with the microparticles, and then the dexamethasone will be released accordingly. Okay. Now, after looking or talking about the example, I hope that we could appreciate this graph. This graph shows the drug concentration in a plasma inside the body as a function of time. Now we have what is called therapeutic window, which is a concentration of drug less than MTC, and higher than MEC. MEC is minimum effective concentration, and MTC is maximum tolerable concentration. Above the MTC, the drug becomes toxic. Below the MEC is not effective. Okay, now to have the constant concentration in the plasma, we need to have zero order release. Now, if we compare the zero order release and constant concentration in plasma, this curve, this red curve, please compare with the oscillating release if we have multiple dosing. Like we have to take pills 3 times a day, sometimes we forget it, or sometimes we have to have injection. But if you have implant inside your body, you don't want to, you want to be healthy. But if a patient has an implant and then he or she doesn't have to do anything, and the drug will be released in this fashion. Okay, we come now to the case 3, extended release from nanoparticles that has been modified with a cationic surfactant. People with diabetes could develop what is called diabetic retinopathy. This is a blood leaking blood vessel at the back of the retina here, and it could lead to blindness. So it is various disorder, and then a doctor could give you or give the patient, not you, intravitreal injection. But of course, it will be a frequent painful injection, expensive. There's a possibility of infection or maybe retina detachment. Now, the better way to do is to inject nanoparticle into the vitreous, the solution here, and then let the drug release slowly from the nanoparticle. Now, there's another thing that we have to know, that the rate of mass transfer or rate of water transport in vitreous is very high. That's the body mechanism and the mechanism in the eye to keep the eye from becoming infected with toxins. So water come and go. And also the nanoparticle. Now the way to solve this problem is to attach the nanoparticle to hyaluronic acid, thing like a protein, inside in abundance inside the vitreous. This is what we try to do. So we have nanoparticle encapsulating a drug, and then we attach cationic surfactant having a positive charge, let's say, and we expect that this positive charge will interact with the negative charge present in the carboxylic functional group in hyaluronic acid. If this happens, and then we could expect that the nanoparticle will stay in the vitreous and do its job, releasing the dexamethasone. We can see from the zeta potential of 50 millivolt that we already attached the DDAB, the cationic surfactant, into the PLA nanoparticle. And here's the dexamethasone release. People has been using PLA and PLGA for so long that there's nothing new about this, that with PLGA 5050 we have burst release. The drug is released practically just in the beginning, or a zero order release when we use PLA. Now we like this release profile. And how about, that's about the drug release from the nanoparticle. How about attachment of how about the stability of the DDAB attached to the nanoparticle? Now this is the plot of DDAB release over DDAB in the beginning. Yes. We could see that with time, we could detect the DDAB in the solution. It means that the DDAB detaches itself from the surface of the nanoparticle, and we don't want that. And to reduce the DDAB detachment, we could increase the lactic acid to glycolic acid ratio, or we could add more DDAB. That's not good. There's limitation for that. And for your information, all cationic surfactant and anionic surfactant, they are, a little bit, they could be toxic. So we don't want to put too much DDAB there. And the best overall result is found for zero order release of DEX for 50 days. And we expect sustained release for 5 months. We could extrapolate. And then the DAB attached to the particle surface for at least 50 days. That's good. So maybe after 50 days, the patient should receive another injection, but not like a week, for example. Case number 4, chitosan alginate microparticles for delivery of mangosteen to the colon area, the colonic area. And we would like to see the effect of the preparation on the release of mangosteen. You see, sometimes if you use chitosan microparticles, not all of the loading or the drug or the active compound is released. Now we are interested to achieve 100% release, and here's the result. The alginate chitosan mesh ratio is important. Alginate will make the chitosan change its property, and we can see here the plot of cumulative relief of mangosteen as a function of time. SGF, SIF, and SCF is simulated gastric fluid, G for gastric, I for intestine, and C for colon. Okay. Now we could see that you could have significant release in the colon, in the SCF, I mean, if you already have release in the SGF. Okay. And we succeeded to get 100% release for this formulation. Now we learned that chitosan and alginate form a polyelectrolyte complex, and this complex, the more the complex is formed, the easier for the mangosteen to be released. Okay, that's the finding. So if you want to have a formulation to treat colonic cancer, and then this kind of information should be useful. This is the last case. Okay. Last case, yes, this is the last case, case 5. We would like to extend the release of anti-TB drugs. You know, TB, tuberculosis. We are talking about spinal tuberculosis. This is for people who has their back, their spinal has been affected by the tuberculosis. Microorganism, and then it's difficult to treat it because the affected area is in the back. It's not easy to give an oral drug because only a portion of the drug will reach that position. Okay, now we want to have some targeted release. And what is shown here is release profile of isoniazid here and compared to the rifampicin. Now you could see right away that rifampicin has a much larger molecular weight and very distinctively different release profile. Now this research has been done only 300 minutes, not very long, but we could see that isoniazid as burst release here, or if not burst released, and then the curve will become flat. In contrast, if you have rifampicin in PVA modified by pectin, and you could see this more or less straight lines that we could expect to be extended for a long time. And this is more like zero order release profile of the rifampicin because this drug has high molecular weight, hydrophobic characteristic, and carbonyl groups that could interact with the added pectin. The result with this particular arrangement or formulation, high loading of the drug and release in the order of months. In the present, we would like to verify our result. And it shows that rifampicin could be released up to 3 months. That's a good thing because up to now only a few days or maybe 1 or 2 weeks release of anti-TB drugs. All right, this is the last issue, multidisciplinary collaborative research. Here's written here, innovative, creative, and useful research result. will take place due to multidisciplinary collaborative efforts, like we are doing right now in this conference, between researchers, especially those in the fields of science, engineering, and health sciences. Because of that combined expertise and resources would enable everyone involved to answer a more complex scientific question or solve problems. And then it's nice to see a problem or solve a problem or see something from a new perspective, because we have discussion with experts outside our fields. Okay, this slide is an appreciation to the researchers and my former students. You can see that I have been fortunate to be able to work with fellow researchers from my own faculty, but also faculty of pharmacy and faculty of medicine. Hopefully, maybe someday I could work with somebody from outside UI, University of Indonesia. All right, this is the summary, I guess. Biodiversity provides a rich variety of medicinal plants as sources of important bioactive compounds. There's a message there for all of us that those bioactive compounds are waiting for us to find them. And then deep addictive solvent, escalin solvent, should be used in innovative application involving extraction and other application. For example, we could use this to absorb CO2 from natural gas streams. That has no relation with health, but solvent, this is a solvent. So we could use this for other purposes. Please promote encapsulation of bioactive compounds or drugs in biodegradable polymer as controlled release formulation to promote health, drug efficacy, and patient compliance. Last but not least, innovative, creative, and useful results will be more likely to take place in multidisciplinary collaborative research, like I mentioned just now. Thank you very much for your attention. And I'm here.
Thank you very much, Prof. Kamarza. It's very comprehensive how you present from the scratch, from the natural, and how to engineer until finally you found ways to apply it in therapeutical and also the clinicals. And I invited all of the participants to put questions in the chat room, in the chat, I mean. And we will move on to our next speaker, Prof. Rifai Chai, yeah, Prof. Rifai Chai. And good afternoon, Prof. Rifai Chai. Yes, do we
Good afternoon, Dr. Yuden.
Yes, Prof. Rifai, how are you?
Good. How are you?
Yes, thank you. I'm good as well. And thank you for your time. So yeah, I've been heard your name several times from my colleagues, but let me introduce you to the participants. Yeah. So Dr. Rifai Chai, Prof. Rifai Chai is currently served in Swinburne University of Technology, Australia. Received the bachelor degree from University Kristen Krida Wacana in 2000s, and then continued PhD degree in engineering from University Teknologi Sydney, UTS, in 2014. And then, he also has working experience as product development engineer in Indonesia and Australia, and then work as associate lecturer in the University of Technology Sydney. And as I said before, currently serve in School of Science, Computing and Engineering Technologies, Swinburne University of Technology in Melbourne. And his research interests covers brain-computer interfaces, medical devices, assistive technology, rehabilitation, signal processing, embedded system, autonomous systems, and AI. At this moment, he is a senior member of IEEE and serve as associate editor for electronic letters. So today, Dr. Rifai Chai will give presentations on the title Toward Interdisciplinary Research of Brain Technology for Medical Devices. So please, Prof. Rifai, the time is yours.
Okay. Thank you, Dr. Yudan, for the nice introduction of me. And thank you as well for the invitation from the organizing committee, ISBE 2021. And I think good day to everyone, for the participant, for the guest speaker as well, and everyone that's joining this session today. Let me share my screen.
Yes, please.
All right, can everybody see the presentation slides on the screen?
Yes, perfectly.
Okay,
Please.
that's good. All right, today I will discuss about the topic of the interdisciplinary research of our research about mainly about the brain technologies. That's for the medical devices. As you're aware, my name is Dr. Rifai Chai. I'm from the School of Science and Computing Engineering Technology, Swinburne University Technology, Melbourne, Australia. And before we talk a little bit more deeper about the project, we go with the definitions of the multidisciplinary, interdisciplinary, and transdisciplinary. Start with the multidisciplinary research. You can see here is basically to like people working together from the different discipline toward one particular project. Now, in terms of the interdisciplinary, is like to basically to harmonize all those like the different discipline to make it working in one particular project, as you can see. And the transdisciplinary is like more towards creating more different projects. It's like a unity of the intellectual frameworks beyond the disciplinary perspective. And there's a motivation for the interdisciplinary research. For example, sometimes there's a policy issue as well as there, and different projects, transportation, for example, biomedical, environmental, etc. And of course, these days, every research tends to be more multidisciplinary, interdisciplinary, and transdisciplinary research as well, if you're aware, because of this new era, digital data, mathematical, we need mathematical, we need AIs as well, we need the modeling, statistical analysis. So most of the research, I think, tend to be multidisciplinary or interdisciplinary research. And there's a required skill as well. It's not that easy to combine the different discipline into one research. We need a common understanding. So the language is important. The way we talk to other disciplinary is normally is based on a particular project when we work on one project. So we can have the common language to speak about the projects and make the projects successful. And the way the research, the method, etc. as well. And sometimes we have to be tolerant with the ambiguity because it's not that easy to combine different disciplines. There's a lot of ambiguities in discipline to understand each other. And sometimes in terms of the personality is important as well to make it happen. Okay, and of course the willingness to work together in a discipline. Myself as well, actually, I tend to be more multidisciplinary or interdisciplinary in my field. So I combine a lot of multidisciplinary skill myself into the project. And this is about my research. Mainly, we start with the biomedical engineering, so medical or health applications. But it can be combined in other kind of discipline, for example, from mathematical, statistics, electronic, when we design a medical devices, we need electronic, we need a hardware as well. If it is a robot, we need mechanical, mechatronics skills. Computer science, but programming, AI, computational intelligence will be there to help us. Neuroscience, one of our application in the brain technology. So we need that skill in the neuroscience as well, or there's people in a neuroscience group to join us to work together in one particular project. And of course, the other application is in transport. Because I have one application toward the transportation as well, particularly with the driver. So today I will explore with 3 projects. One of them is for the medical, for the hypoglycemia. So hypoglycemia is a low blood sugar. So people in hypoglycemia. So I will discuss in more detail later on for this topic. And second topic about the application in transportation, which is the driver fatigue, which is important topic for that need to be addressed in transportation. And the last one is the brain technology for the helping people with disability, so to control wheelchair basically. Okay, let's start with the hypoglycemia. So in here we'll explore from the interdisciplinary research from the medical or biomedical, neuroscience, mathematics, and computer science. You can see all of this research we just based on the brain technology, which is the non-invasive brain technology using the EEG or electroencephalogram. So basically, this is a medical term, or in hospital we can find that one already. Is basically measuring the brain activity through the electrical signal. It's a non-invasive, and it's pretty safe for us to become more practical later on. There's a few publication here you can have a look, the recent publication. There are a few more in the back, so I just put the recent one as well. And basically the hypoglycemia is low blood sugar, because it's quite dangerous when there's people who have the diabetic, they tend to have the hypoglycemia and become more dangerous during the sleep, because they can just turn into coma when they have the hypoglycemia or low blood sugar. There's a definition of the low blood sugar here, the label. The one that we use standard from American Diabetes Association, like below than 3.9 millimole per liter is categorized as a hypoglycemia. And there's a way to measure hypoglycemia. Most common way, we just take a blood and check the glucose level. What will be a problem during the sleep, because people have to wake up all the time and have to check the blood to make sure they're not turn into the hypoglycemia. And that's why our research tried to use a non-invasive glucose monitoring. We've done it in the past through one of them through the ECG. And so few publication from us in the past for ECG. And the recent one, we used the brain signal through the EEG. And we've done the clinical trial. That's with Perth Children's Hospital. So there's a protocol of the clinical trial. You can see different stage, baseline, euclycemia is that normal, blood glucose, RAM, and the one that we after is the hypoglycemia. And there's another session for the recovery as well. And of course, we're measuring the blood glucose at the same time. So they have, actually we monitor them like 24 hours in the hospital condition. And we use the EEG, that's the main purpose of this this research at this stage. So this is the channel of the EEG they're using on the central area in the middle of the brain, and the back of the brain, that's the occipital area. So total is 4 channels. And after we collect the data, we need to analyze. That's how we use the computational intelligence. And in order to do that, we need to get the features of the data. We need to pre-processing of data, features of the data, and we use the AI to understand, to classify whether it's a hypo and non-hypo. And you can see here, most of the EEG research, they always start with a frequency. So we do the same thing for this research. We start with the EEG band. So we concentrate on the delta, theta band, and alpha and beta band of the EEG. You can see there's different range of the frequency for EEG band. And further down, one of the paper we explore what sort of features we can explore, but still around that frequency. So you can see one of them is the centroid. And let me go. This is the features that we explore. This has been published before. So not just using the normally EEG frequency, we use the power spectral density, but we explore different features in that power spectral density. For example, the centroid frequency, the duration, there's a formula how we get things, that one as well. There's a duration radius and the skewness. And we combine these features, and after that, try to train that features into using the machine learning. So at this stage, we use the Bayesian neural network to train the data. There's a mathematical model for training of the Bayesian neural network. And for this research, the performance metric that we use is sensitivity and specificity. So sensitivity is basically a true positive rate, and specificity is a true negative rate. You can see how we get that calculation here. And this is one of the results. You can see from the data, we have we get the data from 8 patients. And from there, we can get around 87 hypoglycemia condition and 94 for the non-hypo. From there, we're gonna have we're gonna do a machine learning and try to learn from data in order to predict how accurate we can classify between the hypo and non-hypo. So you can see on the right-hand side the blood glucose of the patient. And we, as I mentioned before, we use a standard of below than 3.9 millivolt is categorized as hypoglycemia. This is the statistical significance for the features, as I mentioned earlier, that we try to explore different features, and this is the features, the statistical significance of those features. You can see some of them have the very significant that we can use to classify between hypo and non-hypo. This is the same thing. This is for different bands. So this is for alpha band and theta band, and 2 of the band that we can see that have most of the significance. And this is the classification result. And if you're using a Bayesian, if you understand that Bayesian network, we can get the optimal structure. So this is the optimal structure of the Bayesian. We can, from the optimal structure, we can find out what is the best hidden nodes. You can see around that four hidden nodes is get the best result on the training. Then we apply it for the testing. So on the right hand side, you can see on the result on the testing set and training set. Normally we always look for the testing set of the result, and you can see we compare the proposed combined features with other features there as well. The one we propose, we get the sensitivity up to 82% and specificity up to the 52%. Okay, so that's the research on the hypoglycemia detection. And the second project is about the driver fatigue research that's applied to the transportation, if you can see here. So it is the same thing. It's an interdisciplinary research. First thing is in the application of transport engineering, transportation, biomedical will be there as well, neuroscience, because we're still using the EEG. Of course, same thing as we use the machine learning, mathematical and programming in terms of the computer science. And this is the publication that we have published in a journal and also conference paper as well there. Driver fatigue is important in transportation because during the driving, monotonous driving, people tend to get fatigued, get tired. So one of our research is we try to explore using the brain technology, and this stage we're using the EEG, try to detect whether we can classify fatigue and non-fatigue conditions. And you can see here, there's a different way to measure fatigue if you search into the publication. Normally for science, they use when they collect the data, they use a self-report psychometric question, but this will be a problem to do a practical, because it's not that real. It's not that real time. You know, you have to fill up the questionnaire. So we need to find some automatic measurement of driver fatigue. So one of the other methods, they use physiological measurement, tend to use video measurement. So you can find already in a car that some cars have that video to detect the face or the eye blinking. That's for tend to measure the driver fatigue as well, or how tired that driving a car. And in a research, they can use ECG as well. The heart rate variability, the ECG is a heart signal. They can use that one to measure fatigue. EOG is the measuring the eye blink. They can use the same thing for the measure fatigue. But what we want to explore in our research is using the EEG, the brain signal. The idea is the brain signal, because it's linked to the other studies, is like a sleep study. It's like more about the understanding the brains, linked to what is the insight and how that person thinking in the brain will have more interesting features linked to that driver fatigue. And this is the general structure that how we analyze the driver fatigue. It's pretty much same like before. We collect the data through the EEG with the driver fatigue protocol. And after that, using the computational intelligence, it's composed of these pre-processing, because we need to clean out the EEG signal. There will be a features extraction there as well, and machine learning to classify between at this stage fatigue and non-fatigue. And in a real time, that's the idea. If we can classify the fatigue and non-fatigue, then we can give feedback to the user, like alarm, to user to wake them up that, or the idea is later on will be prior to fatigue, like not the onset, like earlier detection of fatigues will be more beneficial to the project, to the transportation area. So in this research, we collaborate with other universities, Sydney University. So they've collected the 32 channel EEG driver fatigue. So we've got the data, 43 driver participant. And this is the EEG signal and what sort of measurement that we use in the EEG. And this is how the EEG signal looks like. You can see it looks like a random signal. And this is the channel that we use, all the 32 channel. And for this experiment, we use a simulator. That's the simulator that we use, a divided attention steering simulator. And there's a protocol to make sure they have to drive, conducting the driving. The participants have to make sure they keep in the middle of the road. And there's a condition how we will stop the experiment as well. If we found that fatigue has happened, we will stop it. Or if they're driving deviation greater than 15 seconds, and we will stop. And of course, if there's a limit of the maximum to avoid for this experiment as well. And after they collect the data, we need to validate the fatigue conditions. This is one different method to validate the fatigue through the video monitoring, through the performance decrement, and of course, we also collected that psychometric question as well. So there's a scale we can double check whether they are fatigued and not fatigued. The same thing like before in other project, we do pre-processing, because the main idea here, we need to make sure the data, we have to remove the artifact, the noise signals in the EEG. So there's different methods. So in here, we use what we call a second order blind identification to remove all the artifact from the EEG signal. And one of our publication, we explore features extraction as well. and we explore through different features. Power spectral density is very popular in EEG, and our one in published journal paper, we use the auto regression model as well instead of using that one. But in the publication, we do comparison as well of the result. And the classification, the machine learning algorithm, same thing like before, we use a Bayesian neural network, but also we use the deep learning. So one of the other journal paper, so we propose what we call sparse deep belief network is a deep learning neural network as well to classify the driver fatigue data. This is the structure of the driver fatigue. The machine learning, the deep learning machine learning. So it's quite different than convention neural networks. You can see they have the discriminative and they have the generative model. That's what makes it different. And the performance measurement for this project is sensitivity, specificity, and the accuracy here. And this is the optimal structure, because we need to make sure we get the optimum result of the training in order to get the result. And this is the result of the classification on different features and in different machine learning as well, which you can see here. Normal convention power densities features, we can go up to 85% of accuracy. But the one that we propose using the AR features and with the deep learning, the proposed deep learning, we can up to 93%. Quite interesting. That's why at this stage we applied to the real time, but still on the simulation. See how good it is. The last project, let me check the time, is about the wheelchair control. So it is the same thing. It's an interdisciplinary research. What I added one here because of this design the hardware as well. So we need the skill of the hardware, of electronics, or the electrical engineering. You can see a few of the publication there as well. So this project is basically the main idea here, some particular disability they call lock-in syndrome. They can't use the hand and the foot as well. The only that's working for them is their brain. So the idea is we use the brain to control the wheelchair for mobility to move around the place, the house. There's a different method already, but we concentrate on the brain because they are locked-in syndrome. And we conducted the trial with the people with disability as well. On the bottom part here, they are on the wheelchair. As tetraplegia, this is the level of their disability from the level C, cervical at the top, so around neck area. I mean, from the neck to the bottom is disabled. And also we collect with the people with healthy participant as well, using the EEG. And for here, we use mental task associations. So different mental tasks. That's the idea. We use the different mental tasks to control wheelchair. Like letter composing, we are set to control wheelchair to the left, arithmetic calculation. We use them to control to the right, rubric cube, moving to the forward, and additional icons to start and stop the system. This is only mental imagination. So it's not, there's no movement of the body. It's basically just imagine those mental tasks. And later on, we're going to use AI, the computational intelligence, to classify those mental tasks. And after that, we use that one in real time to control the wheelchair. So in one of our publication, we use different features, combination of the time and frequency features extraction. And they use the Hilbert-Brown transform. And this is basically how that form of the Hilbert-Brown transform. Okay, and we test that one for the EEG data. So we can see that Hilbert-Brown transform is pretty good to get the alpha. There's easy way to check the EEG signal, because most of the people have the alpha wave during the eye close. So that's why we have to prove that features extraction is working on most of the people with the alpha wave as well. And at that time, we proposed another machine learning using optimization, what we call fuzzy particle swarm optimization with a cross-mutative operation, that to optimize the standard neural network. So that this has been published previously in a journal. And this is the algorithm or pseudocode of that proposed machine learning. And this is the result. You can see here the result of the accuracy. So we have to make sure during the eye close we can detect most of the participants, healthy and the people with disability as well. So they are both 90 or 80% of the accuracy, the detection of the eye close. And this is the comparison of the machine learning comparison between the healthy and non-healthy as well. You can see. And we check with the time as well. They have different time to classify. And this is the result of the classifications. And the one that we propose, the features that we propose, and also at the bottom here, the machine learning that we propose. So you can see around 84% of accuracy that we can use between the proposed features extraction, the Hilbert-Brown transform, and also the machine learning as well. Because of practical, we tend to, because we don't want to use a lot of channel, so we also explore with 2 channel. So at the end, we successfully provide a real-time classification for using 2 channel only, and we on the offline analysis we get up to 80 something%, and also we developed a real-time the EEG system for this purpose as well. Another thing is to make it different, to make it practical. We have the dry electrodes designed for this purpose as well, instead of using the gel, because normally conventional EEG they need to use the gels. So in this real-time application, we use dry electrode EEG, and this is some of the testing on that EEG system. And we do the testing on the people with disability back to do the real-time wheelchair control. And this is the video and how we control the wheelchair basically. So you can see the white stuff there is the EEG that it's a dry electrode EEG, only 2 channel. So we can able to control wheelchair. The speed actually at the moment I use very slow, but we can increase the speed. Okay, let me move to the next one. And for the summary, so I think this is the conclude of this presentation. The interdisciplinary research mainly on the brain technology for the medical device, so EEG in this case. So you can see we use different multidisciplinary or interdisciplinary research group. So the biomedical and medical, basically for brain, using the brain signal, and the application of the brain signal, neuroscience, because of we need to understand that EEG to explore the EEG analysis. So there are a few mathematical model we need to use as well. Statistical analysis we need to be there. Computer science, because we need to program the stuff. Real-time programming that will be there as well in terms of the embedded system we explore. The machine learning, the computational intelligence, we use that, and of course at the end is when we design the hardware is practical medical device, we need the scale of the electronic and everything combined. I think that's it for my presentation. Thank you.
Thank you, Prof. Rifai Chai. It's perfect time. It's really nice presentations, and again, thanks for all of your explanations. And finally, I could see how the electric chair really works. And so again, I invited to all participants to raise their questions in the chat, and I will read after at the end of the Q&A discussions. So thank you, Prof. Rifai Chai. We will meet you again after our next guest
speaker. Thank you, Dr. Eden.
Yes, thank you, Rifai. Our next guest speaker is Dr. Izar. Yeah. And Dr. Do we have Dr. Izar? Assalamualaikum, Dr. Izar.
Waalaikumsalam.
Okay, thank you, Dr. Rizar, for your time. And of course, I would like to read your CV for the audience to know you better. And Dr. Rizar Abdul Aziz holds Bachelor Engineering in mechanical, I believe, and also his master study in material science, and also continue with PhD also in the strong mechanical engineering. His experience with the research and development with highly competitive technical expertise and in-depth knowledge in material and processing area. And he also knowledgeable in new product and process development standards and regulatory compliance, and also engaged in rapid prototyping, manufacturing technologies, mostly in the biomedical devices. So he is a motivated leader with strong organization and prioritization abilities. So now his work as researcher in Advanced Manufacturing Technology Center, IMTC, Sirimberhat, which working on, for instance, like the metallic 3D printers and etc. So without further ado, please welcome Dr. Rizar. The time is yours, please.
Thank you, Chairman. And very good afternoon to all. And I'll start right away. Sorry. Can you guys see my screen?
Not yet. Dr. Rizar, is everything okay there?
Bilang ya Pak, apa? Freeze.
Mr. Chairman, I have to quit and restart back. Is it okay? Can you give me 1 minute?
Okay, okay.
Sorry for it.
But I see your screen now, Dr. Izzat.
Can? All right, okay, good. All right.
Yeah.
Okay.
Okay, yes, please.
So we do, okay, yeah. All right, okay. Sorry for the technical inconvenience.
No problem, Dr.
All right.
Izzat.
Okay, I'll start now. All right, my name is Dr. Izzat Aziz, the founder of the company Trinidad Sidang Berhad in Malaysia. And as the Mr. Chairman mentioned before that I used to work as a researcher in Siring Berhad and working on the craniofacial area, looking on the rapid prototyping and 3D printing technology. And as a researcher, and I've been doing a lot of research in this particular area, and I formed a company which is the 3D Gens in 2016. And here we are in 3D Gens. We adopt this 3D printing technology or additive manufacturing technology to create a product, innovative product, which is in the biomedical sector. And for today, I'm going to share with the participants in 3D printing technology, the applications that we use, and also the challenges that we encounter, and a few case studies that we have been doing during our 5 years as a startup company in biomedical devices and implants. And 3D Gens have vision, which is we want to empower doctors, surgeons to use a total digital workflow, adopting 3D printing technology, adopting additive manufacturing technology, adopting 3D modeling, design, and also simulation, and to have a personalized devices, a customized implant or patient-specific implant to be used for the cases in implant cases, in neurosurgery, in maxillofacial, and also in plastic surgery. So our mission is to produce innovative medical devices and implants with highest quality through additive manufacturing technology. This is the company located in.
Excuse me, Dr. Izzat, could you please transform into slideshow instead of the screen? In viewer form instead of the presenter form. I'm sorry, but
this one it.
Yeah, the presentation.
Okay. Let me,
the use slideshow public. Yeah, that one is. Oh,
it is still in there.
Okay then. Okay, please continue then.
Okay.
Yes, please, Dr. Izzat, please continue.
Okay. And our facility, we have a 3D metal printer, we have the polymer printers to actually produce implants and also devices. We have design engineers, we have production engineers that look into particular area in producing customized devices. 3D Gens also have a ISO certification, which is for the medical devices, and a good distribution practice for the implants. And we also registered under our local medical device authority. Having said that, we have to comply in terms of the product certification, in terms of the certification required in the medical requirement for the medical device authority. And if you see from the traction itself, it has been quite great demand from the hospitals and private and also government hospitals that show the increasing use of the personalized or patient-oriented implant devices in this industry. And we have been working quite a lot with the research institute and the UITM and also private and also government hospitals to produce a personalized customized implant. And the technology that we use is the additive manufacturing or 3D printing technology. As we know that the 3D printing technology actually, how you build things, compared to the traditional method, instead of using a substitute process, additive manufacturing gives us kind of a design freedom and also allow us to produce such a innovative implant and devices that can have a similar to the our patient or bone of the patient itself. So comparing to the traditional method, we have like a substitute process, which is using a block of material to remove the material and get the parts that you want. And in another manufacturing method, it has to use a molding, has to use a mold to actually form a shape to the shape that you want. But for the additive manufacturing, it is using a layer by layer manufacturing that use only material that's needed for that particular part. And you can have, if you look at the way that how the manufacturing process is, it builds through a 3D, 2D kind of cross section and stack the layer together to get a 3D part. So the process itself has been in the market since I think 1980s, and has been due to the advancement in the material. It moved from the prototyping to a manufacturing, rapid manufacturing process. So you can have a functional part, and due to the advancement of the material itself, now you can have a functional use part and to be used straight away to replace the bone. And as the process goes, it has to have a CAD data, and it has been converted into STL format, and then into a CAM software to slice the CAD data that you have, and then you can straight away send it to the machine. And mostly it has no limitation in terms of the design that you have, but it depends on the machine that you use so that you can produce according to the shape or CAD data that you have. And it is definitely a good process to have in order to have a complicated or complex structure in your devices for the implant. And this is the process flow, the standard or fundamental process flow that required for 3D printing. And the technology itself has the various technology. It depends on the what kind of energy that been used to fuse or melt the material, and what kind of type of medium or material, whether it is a filament, whether it's a resin, whether it's a powder. So comparing this 3D printing technology, it can show here that you have a material extrusion, which is quite common at 3D printer in the market at the moment, which is affordable price, which is used a filament material and a heated nozzle. When the filament pass through the heated nozzle, it melts the plastic and started to build the part layer by layer until you get your 3D part. And for a powder bed fusion, it uses a powder type material. So you can have a polymer powder or you can have a metallic powder, and it uses laser, the energy to fuse or consolidate the powder to create a 3D part. And another method that used a resin or photopolymer resin when the light or the laser strikes the resin according to the CAD data that you have, and it built a 3D part. And kind of interesting, another interesting technology is the binder jetting or metal jetting, which is uses kind of a cartridge or similar to the a 2D or Canon HP printer that you have, and you can actually get the multicolor models using this kind of 3D printing technology. So there's a various technology that's in the market that is available, but you have to choose a right or suitable machine or technology to be used in terms of the application that you have. And for us in 3Gens, we mostly use a metal extrusion machine and powder bed extrusion, and also a resin photopolymerization technology to produce the medical application that we have, product that we have. So this is kind of the process that in FDM, which is using a filament material and a heated nozzle. So you can actually increase the nozzle temperature to the glass concentration or the melting temperature of the material, and it's going to melt the material, and then start to lower down the platform and build your part with a layer. And another process here, which is use the resin or wet photopolymerization, and use a optical scanning or optical system to actually scan or laser to hit the optical and start to strike the resin to build powder. So these two machines have a different, even it can build a 3D part or 3D part, but it has a different kind of material and also the print quality. If you look at the FDM itself, can give you 150 micron print quality, but for the SLA or the one that use the resin can give you almost 50 micron print quality. Now, in terms of the mechanical properties, metal printer gives you a quite comparable properties compared to the forging or casting with a good yield strength. But on the elongation part, elongation percentage or ductility, kind of a lower percentage. And due to the process itself, you can see that the material properties, the mechanical properties, the strength, compressive strength is good, but there are certain applications that require, like for the medical devices, you need to have a ductility around 8%, and for that kind of application, we can do a post-treatment to have a to suit the requirement on the ductility part. So that sometimes in medical device, it requires to the doctors to bend the plate or tweak a bit the plate. So with the good elongation and ductility, it allows the surgeons to do that kind of operation. And the good things about 3D printing is that it gives you the freedom in terms of design. You kind of have no limitation in terms of design, but still depending on the machine that you have, and also you can actually incorporate a lot of design, like a lattice structure, so that you can build, because 3D printing allows you to create an internal structure, and you can actually put in a lot of unit cell structure, different structure, in order to increase the also integration when you create an implant. So that's kind of the advantage of 3D printing. Even the speed for 3D printing kind of relatively slow compared to injection molding or machining, but it allows you to have a very complicated design, and also allows you to have the implants that personalized or customized to the patient. So that kind of suitable nicely the technology itself. You can't actually produce a mass customization. You can mass production, but you can have a mass customization in terms of patient-specific implant. So in 3D Gens, we focus in the craniofacial bone replacement, which is on the craniofacial part, which involves the bifrontal, which involves the midface, and also the mandible construction. And definitely, before we can do these kind of implants, we need to look into the appropriate material that can be used with the machine that we have, and also that is suit with the medical or the implant requirement in terms of biocompatibility, bioinert, and also bioactive. And we also to think about how the surgeon's going to be use this kind of implant in terms of the stretchability, whether the material that we use can stain or can be placed in autoclave before it can be used in the operation theater. And whatever design that we do, we have to make sure that it is manufacturability within the system or within the machine that we have. And there's a lot of things actually you can do with this 3D printing technology, whether you want to have and recently there's a company that actually print an organ. And for us, we focus on the bone replacement and also a prosthetic bit. But almost 80% of our product is for the bone replacement. And in terms of producing a bone replacement, there are 4 critical areas that we're looking at. And the first part is that on the medical imaging, on the data acquisition, and then on the material selection. And also the material selection is actually based on the surgeon's or doctor requirements. Different part of bone, different part of face area require different set of material suitable to be used. And from the material selection, we then look into the machine or 3D printer machine selection, whether we can process this material. Certain machine also has its own limitation depending on the material that can be processed, size, fill-up size. So we have to choose the right machine for the right application. And then the design consideration. When we look into incorporate a lattice structure, we have to look into the smaller size that we need to build, and also the size of the implant itself. And so what else that we can incorporate in terms of having a low weight, lighter devices. So that kind of 4 things, 4 areas that we looking at before we can produce the implant itself. And the first part is that to establish the digital workflow in terms of the data provision. What kind of data is required in terms of producing a cranioplasty implant, and what kind of data required in terms of producing an orthopedic implant. So we have to get into communicate with the radiologists and ask them to in terms of the scanning parameters for the CT scan, or what kind of slices that we need, and then looking into the application, like for the orbital floor, we need to have a slight thickness between 0.5 or 0.2 until 0.75 mm. So this kind of information we give to the radiologists so that they can actually set the parameters right, and you can get the the good quality of medical data. So that is very important to get a good high possible resolution medical data, so that you can convert it into a 3D model, then train with a good quality. So once we get the CT scan, MRI, or a 3D scanning data, and then we're going to use a specific medical software to actually convert and do a 3D modeling and simulation. So, and then the engineer will start to design the implant, and will communicate with the doctor surgeons to show how the design look like and how the implant is going to fit with the bone, and before we can actually send to them. And also based on the material that we use, whether this implant needs to be sterilized using the autoclave or gamma sterilization. So it will be decided based on the material selection of the implant itself. So, and the first critical part is on the medical imaging part, where we have to get the the highest possible quality. So this will reflect the print quality of the data that we have. And it is also give a good, if a good 3D model will give a good information to the surgeon in terms of the best approach and how to actually plan for this particular surgery. So in medical data imaging, we use a specific software to get the thresholding value right and start to convert the 3D part of the bone and also the surrounding area before we start to design the implant itself. And after that, we will convert this 2D data with 2D data into a 3D data and simulate the modeling. As the model that show here is the brain cranial-based brain tumor cases, where we model this implant with the brain itself. And in this particular case, the surgeons try to find a way where is the route or the path, the best path to actually approach the tumor. And from the modeling that we send, so the modeling and submission is a part of the services that we provide to the surgeons for the surgical planning. So once they have these models, sometimes they ask for the physical model. So it gives them a bit of a good feeling in terms of what kind of what size of the tumor, and also then try to simulate it physically and do a practice before they go into the operation theater. So 3D analytical model is another thing that it gives you a good insight on the cases before you can plan the surgery. And based on the models that you want, and it reflects to it can you have to choose the right 3D printer machine. So as the first one on the orthopedic, you can actually print out using a FDM technology or FDM machine. But if involved with the multicolor or transparent models, you have to use a inkjet printer or SLA type of 3D printing machine. So depends on the application that you want to have, then you can choose the material and also the machine that is suitable for that particular application. So if you look at this, every application has a different material that can be used. And for us, for the implants, we normally use a metallic and also a polymeric, which is the PIC and ultra high polyethylene. And this is quite important once you decide the material that you want, and then you have to look into the machine. So material selection is important because every machine, 3D machine, has its own limitation in terms of material itself. But most of the 3D metal printer now can actually process a lot of materials, which is stainless steel, a cobalt chrome. So you have plenty of choice to use what kind of metal printer that you want to use for to build your implant. And definitely we're going to look into the properties itself and the surface property itself, whether we need to have a special coating which is with the hydroxyapatite or the existing surface roughness is good enough for the to stimulate the self-migration to this synthetic bone. And biocompatibility, and normally we use titanium alloy for the implants that we have for the bifrontal or the craniofacial implants that we use at the moment. And so definitely factor that we need to consider in terms of when we choose the material and we choose the process is that the what is the effect to the patient itself in terms of bone loosening. And when you use metal, you can see the mechanical properties of the stiffness of the metal itself is high compared to the cortical bone that we have, which is with the range of 15 to 20 gigapascal. And when you put titanium, it is 110 megapascal. So this affects the bone loosening to the patient itself. So and for that particular reason, our medical device authority will be asking us to have all these testing to be done before we can actually put the implant to the patient, such as the bioburden testing and cytotoxicity testing. So this kind of implant, we send it to for the mechanical properties, we send it to a company Endolab in Germany to get all these static tests, and also certified lab to run this testing before we can actually put the implants into the patient. As the for the cranioplasty implant, we use 3 or 4 type of material. The first one, which is the most common material, is the titanium mesh, which is the titanium, pure titanium grade 23, and also sometimes use the titanium alloy TI64. And previously, a lot of surgeons, doctors were using a polymetallic metal acrylate as the method of choice. But due to the case study shows that a lot of, because of this PMMA is kind of an exotomic process, it has been a lot of issue with the patient in terms of inflammation and also infection. So due to that, they have changed to a titanium alloy, sometimes using a solid titanium alloy, and sometimes there are few surgeons also prefer to have a mesh type of titanium alloy. And a recent development is that the surgeons interested to use PIC material. So this PIC material is also capable being produced in using a 3D printer, but you have to use a industrial type of 3D FDM 3D printers that can reach nozzle temperature almost like 400 degrees C. So with that kind of machine, you can actually produce PIC material. But after you use 3D printer of producing this PIC implant, you have to put into a kind of a heat treatment to get the right crystallization process for the PIC. And this PIC implant and also titanium implant you can actually use for gamma sterilization. With this size of implant, you can actually choose whether autoclave or gamma sterilization before you can put into the patient. So and materials is one thing, and it depends on also the product or part that you want to build, whether it's too small or what kind of the features that you have And for that particular reason, you have to choose a different type of machine to be used. Like in this particular case, when the surgeons required to have a transparent kind of part, so you have to use the resin. FDM also can produce transparent part, but the resolution is not that good compared to the SLA technology here. So there are a few, if you are planning to have a multicolor, then so you have to use a inkjet printer machine. But the inkjet printer machine is quite expensive to have. But it's possible to have a very good print quality using inkjet printer machine. So depending on that, you choose the machine that is suitable for your application. And we kind of do a summary in terms of what kind of 3D printer machine that is suitable for application that you want, whether it's just for the visual appearance or for functional parts, how strong you want your part is, and based on that, you choose the machine, the 3D printer machine. So there's a lot of machine is available, whether it's industrial or it's a desktop size. And the most common that you can get is on the FDM part, which is within, I think, 1,000 USD. You can get a good FDM printers for you. SLA will give you a good print quality, but the material handling is different, and definitely the machine a bit expensive compared to FDM. So based on the application or based on the product that you want to build, you have to choose the right machine to be used to get the part that you according to your design. So for digital dentistry, because of the small features and very high quality of print required, we use a SLA machine to produce. And for this cobalt chrome, we use a 3D metal printer to print this part. And for the sleeve stainless steel, we also can use a 3D metal printer. At the moment, 3D metal printer that is available is using a powder bed technology. So the material for cobalt chrome or stainless steel is in the powder type. Okay. And design consideration. The last thing that we look into is that the EM design rules. And as you look into the process itself, 3D printing for SLM, for SLA, and also for FDM, support structures is required. So this support structure actually, in a way, affects the surface roughness of your part itself. You have to think how to remove the support structure after you print the part. And for lattice structure or internal structures that you plan to build to incorporate in your devices, definitely you have to think about how to remove the support structure itself. So with the right orientation, right angle, you actually can remove the support structure. And but for the SLM, you need to really play around the design and the orientation and the process software to have the optimal orientation before you can produce the part. So you can do a lot of try and error before you print out in terms of the orientation, but the orientation itself will reflect to the mechanical properties of the implant that you have. So you have to think about which part that you want to preserve, which surface that you want to preserve, which area that you want to have a solid structure, which surface, which area that you want to have a full density part. So you can play around the orientation, you can play around the scanning strategy before you print out the part that you want. So this is quite interesting in additive manufacturing because you can actually do lattice structure and solid part and hollow part together in one design. And it depends also on the application where actually the implant is going to be put into the patient. Like this for mandibular reconstruction, we have a choice of material within to use for the glenoid fossa, whether we want to use a titanium material with the mandible, or we want to use a plastic material. But based on a lot of case study, they show that these using ultra high molecular weight polyethylene is good combination for this mandibular reconstruction, because the wear resistance of this material is very, very good. And compared to the PIC, yeah, you can actually either use PIC or USM or molecular weight, this polyethylene for the glenoid fossa part. So once you decide the metal that you want, then back to the machine that can actually print this material out. So for this material, you can actually use STM machine to print this part. And for this titanium alloy part, you can use a 3D metal printer. And this for orbital or zygomatic bone, you can, this is very thin structure here. So it's kind of very challenging to even convert the 2D Decembera into a 3D Moldera. So most of the time you want to get a missing area because of the thin structure here. So the scanning parameters is important in the first initial step, where you have to ask the radiologist to have very high resolution CT scan error, which is maybe around 0.25 mm, before they can send it to us in terms of for the modeling and also for the 3D part. So it is, yep.
I'm sorry, I'm afraid that we have very limited time and you already consumed all of your 30 minutes. So
all right, okay. Okay, sure. Sure. And all right, thank you, Chairman. I'll speed up to the last minute. And we have been doing also in Indonesia since 2019, and there's a lot in Indonesian in a few hospitals, Dharma Eyes Hospital, Silom, Karawaci, Betsaida, have been using this implant already. And these are some of cases that we did in Indonesia. But all of this been using a additive manufacturing approach or editing or patient-specific that been produced through the 3D printing technology. With this 3D printing technology, there's a lot of things that we can actually achieve in terms of the physical planning, also in terms of the implant quality. And it helps a lot in terms of guiding the surgeons to have a very accurate surgery and the operation for the patient itself, and definitely give a better cosmetic value to the patient. So most of the cases here have been using 3D printing, and the value proposition is a lot. And definitely the challenges is that, to make sure that the surgeons familiar with the system. And it has become a routine in Malaysia that a lot of cranioplasty or craniomaxillofacial surgery being done through this total digital workflow. And as the way forward, believe that the close operation between researchers and industry is really important for us to really produce an innovative product or use this digital workflow or digital manufacturing process. And for that, I'll say thank you.
Thank you, Dr. Riza. We will discuss it later. I think it's very interesting. I believe that let's put in order that we have questions for Prof. Kamarza. Yeah. So let me read it. Prof. Kamarza noted presentation. Could you explain again why that the DAS is more preferable in processing natural compound? Is it due to the nutrients? Maybe it's because of the natural, yeah, probably. And then the second is, please confirm which is more preferable in release, the profile, the zero order or the other one, and why. And then the third one is the mechanism of adsorptions. What is the mechanism of absorption? Is it based on the different charges? Please, Prof. Kamarza. Thank you.
Dr. Yudan?
Yes.
Terima kasih. Thank you for the questions. For the first question, I think the answer is that you could use this or any other solvents depending on your objectives. For example, we know if we use ethanol, it's called universal solvent, it will dissolve everything. But in the case that we talk about extracting palmitic acid from the palm oil, you cannot use ethanol. Ethanol is very small molecule. You could use DES. So DES is preferable because in that case, it has been proven that you could tailor-made the DES. You pick up, you choose one HBA and or more HBD and try. Now, if you choose DES with a GRAS specification, generally regarded as safe, and then you don't have to worry about that or include it in your product, for example, in food. So if you use a safe solvent, and then maybe it's important. In general, DES is preferred over organic solvent because in a large, if you do evaporation in a very large scale, and then the amount will matters. If you evaporate 1 ton of ethanol, the 1 ton of ethanol will go to the atmosphere. Okay, lalu the next one is about zero order. In general, we would like to have a zero order release if we are talking about drug delivery. It means if you have zero order and then the drug or the active compound release is released at the same amount every time. It's linear. But also it also depends on your need. If you think that you need, as a physician, maybe that you need bacteria in the beginning, and then maybe you don't need a zero order release.
Okay.
Now, yes, I think that's the answer for the second question. And for the question, well, we should ask, it's not a simple plus minus charge difference. When you have absorption, you also have entropic effect. You must consider what's on the surface. For in catalysis, maybe there's no charge difference, but the absorption will depend on, I don't know, we can call it London interaction, van der Waals interaction. Once you have a cationic surfactant and it has a very dense, let's say, the ammonium, the quaternary ammonium has a plus charge then, so it will be easier for the cationic surfactant to interact with the negative, with something, a molecule with a negative charge. I think that's my answer, Dr. Yudan. Thank you.
Thank you very much, Prof. Kamarza. The questioner is, I think, students. The name is Khalifa. Thank you very much, Prof. Kamarza, for addressing all of them. And then there is three questions for Prof. Rifai Chai and Dr. Basari was, and also Dr. Agung Samsudin. Yeah. So I will resum them in one set. The first one is Prof. Rifai Chai, how to make data sets in the project from 8 people, hypoglycemia, to differentiate the class or label of the EEG signals, and how to verify or validate the dataset itself. And follow questions: do we need physicians or specialist doctors in this case? And then, could you explain about the 5 stages: baseline, euglycemia, ramps, hypo, and recovery of the dataset acquisitions in terms of time elapsed during the measurement? And then from Dr. Agung was asking to Prof. Rifai as well, is there any basis on selecting channel for its applications? So that will be the questions, Prof. Rifai. Could you please address them?
Okay, thank you, Dr. Yudan. First question from Dr. Basari. So I think I'll answer this one in a random order. Hopefully I can answer all of them. So start with a question on whether we use a doctor physician. Yes. This is for the hypoglycemia study for low blood sugar. And for this, because we use a type 1 diabetes patient, so we collaborate this with the hospital. So the hospital we collaborate is a Princess Margaret Hospital. It's a Perth Children's Hospital in Western Australia. And before we're doing this, we have to get approval, the ethical approval from the university and also from the hospital. So, and the question, the answer in that question is yes, we use a doctor and also nurses as well, because of clinical study, and also the experiment it have to be carefully done because we recruited with 8 type 1 diabetic patient. And also this study is a claim study. So what I mean claim study is this is to answer that 5 stage of the protocol of experiment. So claim study means we induce insulin to the patient to become diabetic. So that's why the doctor or the nurses have to monitor all the time. And to validate the things, we take the blood sample. We measure the blood glucose level at the same time as well. This is I think we can check in the publication in more detail. This is we measure that every 5 minutes for the blood glucose level. And the study is conduct the study. I mean the study is for measuring for up to 10 hours measurement during the sleeps. So they're divided into the 5 stage of the protocol. That's just answering that question as well. So they are baseline. Baseline basically is a baseline to just collect the data. We don't use the data from the baseline. Then start from the euglycemia is non-hypo. Is the blood sugar level is higher than hypo, and they're taking the blood sample as well every 5 minutes. They have to measure. They have to monitor, and then from there, starting from the euglycemia, is they start to induce the insulin, because then they can go down. Oh, sorry, that's on the REM area. So when they start to induce insulin, the blood glucose will go down. They have to keep monitoring that one. That is a REM condition. And after that, they tend to become hypoglycemia between 3 to 3.9 millivolts or below. We're measuring around 100 minutes on that condition, so to make sure it's safe. And after that, they go with the recovery. Recovery is then they have to inject some sort of the sugar to make sure the blood glucose going up again. That's our 5 steps of the session that it's a claim study. So we induce the insulin to make sure to go into that hypoglycemia. So that's why I have to be careful with that one as well. And after that, when we talk about how we label, it's about the segmentation of the data is collected. So we label the data hypo and non-hypo. Remember, we have that blood glucose. That's how we can compare it we can label it hypo and non-hypo. It's refer to the BGL data basically. As I mentioned earlier, we take the blood every 5 minutes interval. And further down, if I want to add more for the classification that I have done here, in the past, they are few. I mean, the segment of the data is like I think in the past they are they can measure from the 2 second, they can make it measured in 5 second and also up to 20 second. The one that I mentioned earlier in a presentation and also we published, we actually classified within that segment 20 seconds. I think hopefully that answering all the question from Dr. Basari. Now, Dr. Agung, a bit more general with a different project. So how the vesicle selecting channel. For the first project, for the hypoglycemia, because of the condition, it's a clinical study, and also the patient, we measured that during the sleep. So we try to reduce the number of channel. From the research review, we can see some of the, I mean, on the similar topic of the research, hypoglycemia using the research. Previous study, they measure around the frontal, central, and occipital. So our research, we concentrate using on the central and occipital. We try to minimize the channel. Frontal, we don't want to use that one because to make it practical frontal, then because frontal tend to have a lot of noise. So that's why we don't want to use that one. So we use from the central and occipital on the current stage. Now for the other study, for the driver fatigue, for the driver, the one that I presented, we use all 32 channel. It's more channel because healthy participant is just driving, so easier to put that 32 channel. But later on in the practical, we go down with less channel. That's what we did on the wheelchair control. So wheelchair control started with a 6 or 8 channel because from the study we can use from the central, parietal, on occipital. But you can see in the last in the pretty much the end of presentation, we can get down to up to 2 channel. That's around occipital or central area. That's how I use in the practical is 2 channel. So I think hopefully that's answering all questions. Is there any question that I missed?
I believe that you already addressed them, Prof. Ichai, Prof.
Okay.
Rifai. I'm hoping that yeah, all of the presenter could interact with the other participants if possible. Thank you, Prof. Rifai, for the answer. And lastly is Dr. Izar. Dr. Izar, I did not see the questions here in the notes. However, actually, I found next customer for you, yeah, Dr. Izar. So so we have a students, PhD students came from the School of Medicine here in Faculty of Medicine, and he is working with titanium. So I think I hope that we could talk in back channel afterwards. But
Sure.
However, I think there is also a general questions from him that he could not join today because of he has to work. But from his question, maybe there could you put notion on? Yeah, we have seen that you have the HA, and then the PIC, and then the titanium. And the question is all that components are all 3D printed? That was the second based on my discussion, and the scan the second question was on the scalability. I think it's due to the how fast you could product or something like that. Maybe you could answer.
Okay, for the material, we have titanium, definitely 3D printed, PIC also 3D printed, and for the PMMA, we use a 3D printed mold rather than 3D printed the PMMA material itself. And for 3 material, it is possible. So only for the PMMA that we have to print the molding, the mold part. And the second question is about the scalability, is it?
Scalability. The scalability. I think this is the how fast you can deliver the
Produce.
product. Yes.
Yeah. Okay. So basically, currently we can actually produce the implant, the customized implant. Once we get the CT scan data from the patient, is within 3 days, we actually can produce. But it depends on the which part of the bone that you want to replace. For the frontal part, for the bifrontal or for the lateral of the cranioplasty, it is quite fast because the design it is quite straightforward. But for the mid phase, which is involved in zygomatic bone, maxilla, and also the mandible, it requires at least 2 weeks for design. And within these 2 weeks of design is the communication between the surgeons and also the design engineers. So like I mentioned before, you have to look into the right methods to be used and also the patient condition itself. What kind of example is for the bifrontal, when you have a patient that is very thin skin, thin skin, you can't use a titanium mesh for the implant because you can have a tattooing effect after maybe around maybe 1 year, 2 years after that, you can see the texture itself. So based on the patient condition, based on the requirement on the functional part of the implant that you want to produce, you can actually choose the right material for the particular implant. But for mid-phase or mandible, which is a dynamic implant, which is have a joint, that kind of design require more time rather than the straightforward implant like a cranioplasty. So and then at the same time, if you want to incorporate a lattice structure, or you have a specific requirement, which is you have a target of weight of the implant itself. As for the mandible, the cases that we did a few weeks back, the first design was weight around 42 grams. But the surgeons actually requested to have an implant that is within 15 grams to 20 grams only. So for that requirement, the design engineers start to incorporate the structures to remove some of the material at the available part, and we managed to reduce to 20 grams. So that kind of communication and procedures actually happening that take a longer time to produce. Printing, it depends on the size of the implant or height of the implant. Mostly the printing speed is 10 mm per hour. So if you have 40 mm, it probably took you 4 to 5 hours. But you can't actually straight away take it out the part once it's finished printing. It has a cooling down period. And normally 8 hours is the common printing time for each implant. And once you produce, you have to put into a post treatment, finishing part. So it probably took you 2 days to complete a printing part alone. So add up with the design, the communication for the maxillofacial cases, it actually take 3 weeks to produce.
Thank you, Dr. Izar. It's very interesting. Thanks also for your comprehensive answer. So I believe that it comes our time, and I personally thanks for all of our 3 presenters. They are very great, and I learned a lot from all of them that we should multidiscipline, collaborate, and problem-solving attitude. I think that's what I learned from all of the presenters. I think we have to give our best applause, digital applause to our today's speakers. I do not know how to digital applause. Yeah, again, thank you very much, Prof. Kamarza, Prof. Rifai, and Dr. Izar. Looking forward to discussing again with all of you. And I invite all of our participants to not reluctant to contact our assets today. So that will be it. And I'll come back to Mystica as our moderator. Thank you very much again, everyone.
Thank you, Dr. Yuden. Thank you also to our keynote speakers, Professor Kamarza Mulia, Dr. Rifai Chai, and Dr. Izar Aziz. Ladies and gentlemen, as we have previously announced, Breakout rooms are available for further in-depth discussion with our keynote speakers. Please contact the committee through chat room if you are interested in joining any of these rooms. The secondary plenary session is over, and we will now take a lunch break for 30 minutes and also for afternoon prayers before we start the parallel session. The parallel session will begin at 1 p.m. Indonesian Western Time and will be held in 3 separate breakout rooms. Each breakout rooms for drug development and delivery, medical devices, and biomaterials. Please contact the committee if you are unable to go to your selected breakout rooms. We also advise you to consult our parallel session schedule that can be found on our website, and the participant certificate will be distributed after the conference via your EasyChair account. The committee will also select best presenter, and the award will be presented at the closing ceremony tomorrow. We strongly urge all participants to attend the closing ceremony to celebrate the winners of the best presenter. Now, ladies and gentlemen, before I close for break, I would like to invite all of you to please turn on your camera for a final photo session. Everyone, please turn on your camera because we will have a final photo session together. Mr. Gunawan, are you ready? We have around 3 or 4 pages, if I'm not mistaken. Mas Gunawan, ada berapa halaman? Baik, ada berapa, Mas? Baik.
4, Mbak.
4 ya. Semua siap? Everyone ready? Turn on your camera, face the camera, big smile. 1, 2, 3. And now for the second page. 1, 2, 3. Third page. Everyone, please turn on your camera. 1, 2, 3. And the final page, or the fourth page. 1, 2, 3. Okay, thank you very much, everyone. Ladies and gentlemen, have a good symposia. See you in 30 minutes, and may you enjoy the parallel sessions that we have prepared for you. Good afternoon and take care.